Okay, good morning, everyone. And let's look into the future and think about transportation of goods and ourselves. And let's do that in terms of safety. And with that in mind, you may ask, how should we improve vehicle safety? How should we optimize crash performance in the most sustainable way? And some follow-up question could be, which steps should we utilize when it comes to developing flexible manufacturing methods? How should we develop reliable numerical models for computer-aided design? And how should we adopt economical circle models? And how should we introduce new green novel material solutions? These are some questions we should try to answer today in this conference with the name Shaping the Future for a Safer and Life Automotive Industry, which is a conference organized by the European project FlexCrash. Well, I think it's time to introduce myself. My name is Iber. I'm head of division of solid mechanics here at LTU, and I have the pleasure to both open this and also to share the first session. And if you look at the agenda, you can see that we will start with a presentation about FlexCrash, and then we will also close this conference with another session where we have a presentation for 3 closely related projects. And that session will be shared by Daniel Casellas from Aerocut. And I checked the attendance list this morning. I realized we have a lot of people from the industry, from the academia. I'm very thankful for that. But I could also see that we have students online and here in this conference room. So for all of us engineers, I realized that we could have a challenge here. Is to convince them, the engineers, the students, how important, challenging, and interesting the research about safety in future crash scenarios. So take that as a challenge. I don't want to put any pressure on you, but just a challenge. So then I think it's time for me to introduce the first speaker, that is Simona Neri from Aerocut, which is the FlexCrash coordinator. So Simona, please, the floor is yours.
Okay, so good morning, everyone. Let me just start saying that I'm really happy to be here today, not just because it's our first project public event, but also because we have the opportunity today to share this initiative with the other project that are part of our cluster, one that is funded under the same topic of FlexCrash, that is the Salient project, and then other 2 projects, Salema and Flamingo, with which we have a lot of synergies. So just a brief overview about the project. As I said, FlexCrash has been funded under the topic D60110, that is testing safe lightweight vehicles and improve safe human technology interaction in future traffic system. Our project is a 4-year project that received almost 4 million fundings, and our consortium is composed by 10 partners coming from 5 different countries. So here you have an idea of which is the structure of the main stakeholders involved in the consortium. So we have 3 research centers, 2 universities, 3 industries, and 1 industrial research center that are really driving our decision in terms of selection of technologies and materials, and 1 standardization body as a support. So which is the motivation behind our project? First of all, we are trying to find more sustainable and lighter vehicles. Why? Because we need to support and to meet the greenhouse gases emission target of the European Commission, that is the reduction of 30% by 2030. But making cars lighter is super important, but we need also to make sure that they are also safe. And everything must be aligned with the European policies, and mainly the Circular Economy Action Plan and the European Green Deal. So here you have a FlexCrash ambition. As I said, we want to develop a low weight and circular cars, keeping safety and the reduction of injuries due to crashes, and also meeting the EU-term goals on zero emission. So which is our solution? Here I divided it in four main areas. The first one is the manufacturing technologies. Then we are also approaching digital solutions. We are working on materials, and we finally validate our developments in a demonstrator. So speaking about the manufacturing technologies, here we are proposing flexible hybrid manufacturing technologies that support us to create a tailored adaptive crash tolerant structures. Here, we use the performance extruded profile and the high-pressure die casting component that is coming from a project that will be presented in the second session. And the added value functional feature are added by laser metal deposition. Here you have a screenshot of our production process in EuroCAD, and also a brief explanation of the additive manufacturing process. So we are also proposing a digital technologies. Here we have an online platform that allows different players to interact live, and this support us to identify critical mixed traffic scenarios that can come in the future when we are going to bring lighter vehicles together with our current ones. Materials. As I said, we want to make the cars lighter, so we are going for aluminum-based alloys. So here you have three different steps, because we are selecting aluminum because it's lighter, but also because it can be recycled. So when we are going for recycled aluminum alloys, we go for three different steps. So that's the selection of the different aluminum scraps, then the addition of specific elements in order to avoid the formation of brittle phases, and finally the adjustment in order to hit the mechanical properties that are needed for our scope. And here you have our demonstrator. As I said, it is based on a performance extruded profile that comes from Salem. And here we add by laser metal deposition some specific feature, and our main scope is to make it lighter and also capable of responding to the crashes that we are testing. So the project phases are mainly three. The first one is to collect the crash information through the platform that we have been creating. In that sense, this helps us to understand exactly which will be the most probable future crash. Then we are going for the development of the different materials and technologies. And finally, we will have our validation phase. We are currently in our first year and a half, so the first reporting period, and we are already finalized the first phase, and we are already working on the second one. And we are happy to share today all the different details of the different topic I've been speaking today with the next speakers. So thanks a lot.
Okay, when it's time for the first session with the name Towards a Safer and Lighter and Circular Crash Structure Production. And as you can see, we have 1, 2, 3, 4, 5, 6, 7, 8 presentation, if I count it quickly. And the procedure is as follow. Each of them will present, and then we will end this session with the questions and answer at 11:25. So we won't have questions directly afterwards. So you who's participating online, you could write your questions in the chat, but please address also who you would like to ask the question. For example, Simon and so on. And for you who's in this conference room, if you will have a question, raise your hand and then unmute your microphone. You have a button in front of you. ask your question, and don't forget to mute again after that. And I will try to keep a balance between the questions in the room and the questions online. So that said, it's now time for introduce the first speaker, that is Simon Jonsson, which is a PhD student at LTU, and he will share this presentation together with Daniel Berglund from Aerobase Innovations. So welcome, both of you.
Okay, thank you for that introduction, Jörgen. As I said, my name is Simon Jonsson, and I'm here with Daniel Berglund. And we're gonna talk a little bit today about advanced material models for crash scenarios. I'm just gonna get. So I'm gonna start off a little bit just with a brief introduction, and then Daniel is gonna take over with material models for aluminium high pressure die casting. And we're also gonna set some conclusion and future work in this project. So a quick introduction just to give some context on what we want to do. It should come as no surprise as vehicles are becoming bigger and heavier. You see the past decades there, you can see a huge increase of SUVs. We like bigger cars. We like to have more things in them. So they are naturally becoming bigger. And this, of course, negatively impacts the European long-term climate goals. So we want net zero even greenhouse gas emissions by 2050. And the transport sector is basically the only sector that hasn't reduced its greenhouse gas emissions since 1990. So this should be a huge focus area. But even this, of course, applies mainly to the internal combustion engine vehicles. But even for vehicles that have other powertrains, like electric vehicles, when you think that this lightweighting that maybe doesn't matter that much, it's still problematic, because you can see there in the circle there that heavier vehicles leads to increased momentum, more severe crashes, and heavier and safer structures are thus needed to protect the passengers. And you can see these circles around leads to heavier vehicles and all that. And also electric vehicles have these very sensitive batteries that you don't want to break because it gets really nasty fires. So lightweighting is still necessary, and we of course don't want to compromise crashworthiness. And here in the FlexCrash project, we use aluminum alloys, such as high pressure die casting, that you cast large lightweight parts and extruded aluminum, and then you can use additive manufacturing to allow for low weight and optimize crash resistance by locally reinforcing critical areas. So basically, we want to break that cycle. We don't want to increase the weight, but we want to have better crash safety in our vehicles. So it should come as no surprise that full-scale testing and testing crashworthiness is very expensive and time-consuming. It's also very limited to the amount of scenarios that we can test, because it's very complicated to set this up. So, of course, numerical modeling is essential in the automotive industry today, because we can try different scenarios, basically whatever we want in the virtual realm. So this allows engineers to test the feasibility of their designs and virtually different crash scenarios before creating prototypes for validation and implementation. And here in the FlexCrash project, we focus on the front end. Because it's the main problematic area. I mean, 70% of all the crashes are in the front of the vehicle. So this is an important focus area. But of course, we need to be able to trust our numerical models. So accurate material models and failure prediction, which can negatively influence the component design, is very important. And in this project, we use aluminium. And one of those techniques that we use is the high pressure die casting, that we cast our parts. And this introduces some challenges, because we have complex phases and intermetallic phases in homogeneity. We have porosity as cold flakes, shrinkage, inclusions. And we have also material property gradients in this thickness. So this is hard to model. So the aim that we have here in this project is to develop a combined deterministic and probabilistic model for the high pressure die casting components, deformation, stress, and failure, including microstructure effects with focus on the grain size distribution. And to talk a little bit how we're gonna tackle this, I will leave over to Daniel here.
Just to repeat a little bit about the material model, what is that? That's, you can say, a mathematical description of how the material behaves. And usually you have a lot of different phenomena, but in this project and with high pressure die casted material, we will focus especially on the effect of the grain size. As you saw in the picture before, you have quite different grain size on the outer surface of the component and in the center, and this needs to be taken into account. Even if we create a very good physical base model, we will always require material testing. So in some cases, it can be a little bit more advanced testing with higher strain rates, but that needs to be included, even if we know the microstructure. So if we look at the mechanical properties of high pressure die casted material, this is a typical stress strain curve. If you test a number of specimens, you will see that you have quite small variation in the yield stress and ultimate tensile stress, but you have quite large variation in failure strain. As you can see here in this example, you have a variation between 11 and 16.5%, and you need to take care of this. Of course, you can be very conservative, design your system for 11%, but with more samples testing, you will have your lowest value will go down more than that. And that's the reason why we have introduced something called probability. Deterministic modeling, then you have one value where you get failure, but including probability means that you can calculate the probability of failure. So as an example here on the right-hand side, we have one element. I don't know if the animation is running. No, not. But if you deform this element, so on the x-axis, you have the equivalent plastic strain versus the probability. So in this case, it's a material with 12.5% of elongation or strain for the mean failure. So you can see when you reach 50%, then you reach this failure strain. 50% probability, that means that 50% of your specimen will fail when you come to this deformation. Another thing with failure strain is that it is dependent on your stress state. So we usually define it with something called the stress triaxiality, and that is the stress condition. So typically in a uniaxial tensile test like this, where you have a hole in the center, then you have a value of 0.33. And then if you have more shear-like behavior, then you close up to almost 0. And in plane strain condition, you have approximately 0.58. So you need to create these failure curves. This represents the failure strain at that current stress triaxiality. And you need to take into account the microstructure. So in our case, it will be different on the outer layer of the component and in the internal part of the component. And another challenge is the variation in failure strain that we need to take into account. Let's say that we test at a certain stress triaxiality, we get variations, but we don't have the same variation at another stress state. This needs to be taken into account, and that's one of the research questions we try to solve now in the FlexCrash project. So the dotted line represents 3 standard deviations from the mean value. So our hypothesis is that when you calculate your failure strain, because this is dependent. In a crash analysis, you don't have a constant stress triaxiality. It will vary, so you need to take care of that. But we do that, you can say, linearly. So as an example here, if we start with uniaxial tensile at time T1, we deform it, and we are 40% from the -3 sigma line. Then when we go to the next time step with another stress triaxiality, in this case, close to plane strain, then we start at the same, you can say, distance from the -3 sigma line. The other condition is that when we deform more in the first step, so we pass this -3 sigma line, then we are in the world of probability. So we need to take care of that in another way. So what we do then is that we follow the isoline. When we then change the stress triaxiality, so it's this, we move, so we have the same, we start with the same probability in the next step before we take that additional strain step. So that's the hypothesis, and that's something we need to prove in this project. Just to show you an example, this is a bending case. So when you post-process this is an example where we have implemented in Dyna. But now I think I will try to use, if we can start is it possible with the mouse to try to switch that? As you can see, when it changes color with probability, so 1 represents that all components have failed. So in this way, you can basically, when you design a system, you can choose at what probability will I design it for? Will I take the risk to have 10% or 20% or 50% when I design my system? So what we also have done to be able to resolve this very thin layer of small grain size and the component, if you use a solid model, for example, it becomes a very small element. The green area here, you can see that it's elements that are 0.1 millimeter. The time step will be extremely small in an explicit crash analysis. So what we propose is that we use something called thick shell, where you can define your material properties in different layers. So then you can easily include the skin effect. So in this example, I will try to start that. On the right-hand side, you have the thick shell model. It gives similar deformation behavior, but in this case, 17 times larger time step than the solid model, which saves a lot of time. Of course, when you do this discretization, you need to be accurate. So this example shows the force versus displacement. And as you can see, with one element, one T-shell through the thickness, we cannot really resolve the force displacement result. But with only 2 elements in the thickness direction, we can get approximately the same behavior as with the solid model. So if we talked about AM in the introduction, you can also introduce AM structures in this by, we also propose here to use this thick elements for that can be modeled. So if you look at some of the conclusions, the probability model has been implemented. You need to include the stress state dependency. The standard deviation at different stress states can be taken into account. Thick shells are very efficient for this kind of structures. And where we think 2 elements is enough through the thickness. And the next step and future work will be calibration of this model. That's the next step. So I think I will stop there.
Thank you very much, Simon and Daniel. A very interesting presentation. And if I could have a look in the agenda, we could see that the next speaker is Sergey Rader from Educat. So please enter the stage.
No, perfect. Thank you. Thanks for the introduction. So here today we will see the different techniques that we developed and that we will use in the FlexCrash project to characterize the materials in different situations, in case of durability, but also crash. So the main idea is to have different tools to assess the behavior of these materials, to design and also to select the best material for each application. So the main structure of this presentation will be like, we will first address the vehicle lightweighting, so why it's necessary to reduce the weight of the vehicle, then the passenger safety, the vehicle durability, and finally the material selection, which strategy or how we can use this knowledge here to select the best materials for each application. So regarding the vehicle lightweighting, as we already seen in the Simon presentation, the main trend nowadays in the automotive industry is that the weight of the vehicle is increased due to the utilization of these batteries, right? So you can clearly see here in all of these different vehicles that the weight of the main vehicle is increasing about 15 to 40%. So then it's clear that, well, if we want to optimize how these vehicles perform, we have to reduce the weight of the vehicle to increase the range of the vehicle and also to make them much safer. So here then we have these different structures. We have the body in white structure, but also we have these chassis components that we can address in order to reduce the weight of the vehicle. So nowadays in all of these vehicles, we have this well-known banana curve where we have all of these different materials, high strength steels that are used to manufacture all of these different components. And I put here example of the Tesla Model 3 where we have all of these different components. So at least 171 pieces is made of different high strength steels. But the trend makes sense to use a lighter alloys, so aluminum alloys, and also use the technology to reduce such amount of components in two big components. So the called and the popular giga castings from Tesla. So in this case, we are moving from almost 200 pieces to 2 pieces of aluminum. And this is not extraordinary. I mean, the main trend in the car industry is to use this technology, this giga casting. So you can see here all of the different brands that are using or that they're planning to use this technology or they are investigating this technology to produce these vehicles. Then, well, in the FlexCrash project, we are well aligned with the main trend and the future trends in the manufacturing of the vehicles. So, but let's talk about the passenger safety. So in this case, you can see here this picture from a Tesla vehicle. So here we have this cast part, then we have this front rail and the bumper. And this structure is very, very similar to the FlexCrash structure where we have also this cast part, the extruded rail, and then the bumper. So it makes sense to characterize the behavior of these materials. And we're looking, for instance, in the case of these front rails, here you can see a clear example of how the material properties, how the material structure affects the behavior in case of a crash. So here, this is a clear example where we have compressed, where we tested these two different extrude profiles at the same intrusion. And here in this case, we have this, I would say, like this brittle behavior where the material is totally destroyed. And then here in this one, we have this folding behavior. So we have this smiling face here. So the behavior is totally different. And we want this behavior because is when the material absorbs a lot of energy and we are constructing a might safer structure. And how we can evaluate or identify which behavior we will have. So what then we can characterize this behavior by using the fracture toughness parameter. So here you can see the difference in energy at the end required to crack the material. So then let's see the technique that we will use in the FlexCrash project, and that the technique that we are started to use in the FlexCrash project to assess this fracture behavior of the component. So here we are using this technique, the essential work of fracture, where we are testing different dental specimens, these double-edged notch tensile specimens, where we have a different ligament length. So the ligament length is the distance between these notches with cracks, fatigue pre-cracks in the notch, and we test them until fracture. So here mainly we have the different ligament length. We are testing them, and here you can see the load displacement curves, and we are measuring the energy below the curve. So if we measure this energy for each specimen, then we can calculate the energy required to initiate the crack in the material, and also the energy required to initiate the crack in the material, but also to propagate it. So then if we perform this analysis with our materials, the materials selected in the FlexCrash projects, here we have the 6063 and the 6111 in T5 condition. In this case, we just performed the tests in some extruded parts, and we identified the required energy to initiate the crack in a material. Well, we can see that we can detect the difference between these two materials, and as we saw in the previous slide, it makes sense to use the material that requires a higher energy to propagate the crack or to initiate to propagate the crack. So then we will go for the 6063. And here I also put this graph where we are comparing this energy absorbed at maximum intrusion. So this is a case of a component or these extruded profiles represented against the essential work of fracture. So we have a linear trend. So just to show that it's a good property to assess the energy required to crash a component. This is for advanced high strength steels, and I just put it here that, of course, in this case, well, the aluminum alloys are a little bit lower, but we can see difference between these two different materials. So then we have on one side, we have a test, this essential work of fracture test, to assess the crash behavior of the material. So we have a strategy to select the best material for crash scenarios. And then it's time for the vehicle durability. For instance, I just put it here, this picture from the Xiaomi vehicle, this new one vehicle. And well, they define here, for instance, a 2 million lifespan durability. So this means that these components, these chassis components at the end, they have to withstand cyclic loads. So these loading and unloading loads that will be critical in some applications. And in this case, we have different strategies to select the best material for fatigue applications. The most known strategies to use this SN curve, where we have different approaches, the strain life approach, where we have huge stresses, stress life approach, the common one, I would say, and the one most proper to characterize this fatigue limit related to this a lot of million of cycles. And then we have the very high cycle fatigue. That's another stuff. But well, the point is that if we want to characterize or to get this SN curve for a given material, we need a lot of specimens, and also, as you can see here, a lot of time, since only one specimen in this regime of million of cycles takes from days to months. So then we have to consider also that this ascent curve depends on the different conditions of the specimen. So for instance, in this case where we have this AVFF, so this reinforcement in the material, we have to characterize the material with all of these different conditions. And this means a lot of time. And in this case, what we propose and the main idea in the FlexCrash project is to use this new test, the stiffness method. In this case, what we are doing is by only using one specimen, we are applying a different fatigue blocks with an increasing stress amplitude. And during this test, we are monitoring how the damage is evolving in the material. So we are doing this loading and unloading parts here, and we are monitoring the elastic response of the material, the strain response of the material to a given stress value. So at the end, we can monitor how the damage is evolving since this start of the fatigue damage to the micro crack initiation and propagation, and finally to the macro crack also initiation and propagation. So the point is that at the end we get this kind of graph where we have this plastic strain related to this fatigue damage that we are monitoring by using this test. And we can plot this damage against the stress applied in each one of these fatigue blocks. So by doing that, we obtain this curve. So, and we can clearly identify the different regimes. So no damage, these first stages of damage related to micro crack initiation and propagation. And finally, this macro crack propagation in the material. Here you can see these micro cracks in this regime 2, and we are using these points to assess the fatigue threshold. So the point where we start, or the stress level when we detect that something is happening in the material, and then also the fatigue limit. It can be a little bit different. This depends on the material, and so the damage tolerance of the material. This is one approach, but also we can also use another approach where we are defining the fatigue limit, since the first point that reaches the threshold, define it as 10 times the standard deviation of the first point. So this is just a tool to rapidly assess this fatigue limit value. Then we can also use the same data, but in this case we are just switching the axis, and by using this data and applying these general formulas, we can obtain a first approach of the ascent curve, so this basking curve, and define by only using one specimen, define the fatigue limit and also the ascent curve, or at least the first approach of this, to have a first approach of this for these different materials. And the good point is that this tool allows us to assess the fatigue behavior in a lot of different conditions. So for instance, with different materials, but also with different features in the surface or different roughness conditions or wherever. So, and then select the best material for each application. In fact, this is the main aim also of the FlexCrash project, and also to propose and have these new techniques to select the best materials for these applications. And in this case, makes sense to simply use this graph. I mean, here, this is only for these 2 aluminum alloys that we investigated here, or we're investigating here in the FlexCrash project. But the main idea is to plot this fatigue strength for all different materials against the fracture toughness values, and define different regions where we can clearly identify which is the best material for each application. So here you can clearly see that there is a huge difference between the 6111 and the 6063, and makes sense to select this material to obtain this folding behavior during crash, but also to have the good fatigue resistance when we are talking about to use this material for chassis applications. So this is all from my side. Thanks for your attention, and I hope everything was clear, and I'm happy to answer the questions afterwards. Thank you.
Thank you very much. And I think we have one more presentation before they have the questions and answer session. But I have to ask, do we start to have any questions online? Not yet. Then you have some time here to start to put down your questions. We have 50 minutes, so please put down questions. You, the audience, keep in mind what were the questions you would like to ask. Okay, then it's time to welcome Francesco Brusso from Fraunhofer, and he will give a presentation about LMD optimization and reinforcement structures characterization. So please, the floor is yours.
Yeah, thank you very much, Jorgen, for the introduction. So as the speakers before me already introduced, we will have in this project, the aim is to have high pressure die casting parts where we will add by additive manufacturing some reinforcement structures. Yes. So first I will go through very fast on introduction on the laser metal deposition technology, how it works, what are usually isogrids and reinforcement structures, and then how the process parameter development and the specimen manufacturing that we are currently working on in FlexCrash project. So laser metal deposition, it's a additive manufacturing technology that is also called direct energy deposition with the laser beam and metal. And the aim, very similar to plastic 3D printing, is that we have a nozzle through which we have delivery of energy and material that then combine in a melt pool to add then material to this melt pool. With the relative movement between the nozzle and the substrate, then we create some tracks with the addition of material. The animation is not working, but we can have these relative movements. Yeah, that one. Yeah, it's not important. So. By pre-programming then the movement of the nozzle above the substrate, we can create complex 3D shapes. As the previous speakers already introduced in this work, we are working with aluminum alloys, and this presents a significant challenge when 3D printing aluminum, especially with lasers. Mainly for two reasons. One is the high reactivity of aluminum, especially when in molten state with hydrogen and oxygen from the atmosphere. And the other one is from the laser interaction with the material. So as you can imagine, the laser is our source of energy, through which we can control the amount of energy to melt the aluminum. However, the absorption of aluminum material from the laser is very challenging to control. And you will see then the results later. So going more on the reinforcement structures, of course, reinforcement structures is not something new. It's something that is done already, especially in the aerospace sector for many years, because there we need to have high stiff or high strength components with very lightweight in order to save fuel to go to space. As you can see, until now, they were always done with constant and repetitive patterns for which we know the mechanical properties. However, it is still very expensive to produce these components because usually are milled away from a huge block of material, and you have a lot of material waste and high cost. Our aim now is to use additive manufacturing so that we can create different patterns, or we are quite free in the geometry of the patterns that we can print on our components. And you can see from this simulation done by a FlexCrash project partner that by controlling the shape of the reinforcement structure that we deposit, we can control the way a frame deforms during a car crash and the amount of energy that this part absorbs. So development of the process parameters. In our technology, as I said before, we have three main parameters because we need to control the amount of material, the amount of energy that we put into the process, and the speed in which we do this. So of course, the three parameters we want to control are laser power, speed of the movement, and the amount of powder that we feed through the nozzles. Then we have other fixed parameters that depend mainly on the system and the material that we're using. As I said before, in the case of aluminum, also for safety reason of the process, we need to operate under an inert atmosphere with oxygen level below 50 ppm. Otherwise, we risk to create to start a fire with the aluminum powder. Here you can see some initial tracks that we deposited with different process parameters, and then you can appreciate the ratio between the height and the width of the tracks that we deposit. This is something it's really important for us to control, where we want usually a height 1/4 or 1/3 of the width. This is not for any made up value, but because we found in the past, then if we develop the tracks in this way, we are able then to do 3D shapes with low levels of porosity. From the design of experiments analysis, then we can understand the influence of each parameter on the shape of the tracks that we deposit. And you can see that we have a very different impact of each of the process parameters on the shape. So for example, speed and amount of material that we feed through the process have a strong influence on the height of the track, while the laser power has mainly an influence of the width of the track. But very important for this project is the amount of material of the substrate that we remelt to create then the melt pool on top. As I said before, working with aluminum is quite challenging because when we deposit single tracks, everything looks fine and we have nice depositions. But when then we try to build some higher walls, aluminum has a very high tendency of overheating. And this creates, as you can see, balding effects where the molten metal solidifies in this type of balding along the deposition of the track. And also, due to the heat accumulation, you can imagine that the melt pool takes a longer time to solidify. So the molten metal has more time to spread, ending up in wider and thinner layer every time we deposit. With the close-up of the deposition, we could notice already from the beginning that the first track we deposit on the substrate is quite thin, but already from the second track on, we had this effect of the tracks getting thinner and wider. In order to control this, then we had to change the strategy that we use for the deposition. So add more tracks in the initial layers and then reduce the number of tracks in higher layers. From the cross-section, you can see the first results when we tried to have two tracks, one next to the other in the first layer. And here we had to optimize the distance between the two tracks. And our aim then was to achieve a wall with the quite constant width. Here you can see that two tracks in the first layer are not enough. And especially what I was saying before about the problem of overheating. You can say here in the first track that we deposit left and right, the cross-section or the area of the track that we're depositing. In the last layers, due to this overheating effect, the area of the melt pool is almost 5 times bigger than the one in the first layers. So we went further to optimize this, try to have this pyramid shape at the base of the wall that we deposit. And we found out then that the best strategy is to have 3 tracks, in the first layer, 2 in the second one, and 1 further on. In order to be able then in the future to design not only single walls, but also crossing walls, where maybe from the simulation, we will see that this type of crossing walls then can achieve a higher energy absorption during the crash of our components. We also have to optimize the deposition strategy when we have this type of crossing walls. As you can see, in this case, we have formation of significantly bigger pores in the crossing points. However, at a higher level, we didn't have this type of defects. These defects, for sure, are characteristic of the process itself, and we have to consider them during the testing, also then to have the material properties that we will use to simulate the shape of the final reinforcement structures. So the last step and what we are currently working on in the project is the specimen manufacturing as it was presented in the presentation before, and the first trials that we are going to to test, to characterize the material we deposit. So now we used 1.5 millimeter thin thick substrates. And here, as you can imagine, it's really important what I said at the beginning, to control the amount of material from the substrate that we remelt, and to avoid then also to basically cut or go through the thickness of the material. And our aim now is to try to test this material with a 3-point bending test. Of course, usually to characterize material, we do tensile or fatigue testing on bigger components. This could be, however, a problem when we try to characterize our AVFFs. This is because with 3D printing, if I'm trying to print a relatively small but long wall or a big block of material out of which I can mill out my samples, I will end up with completely different microstructures because the material is subject to completely different cooling rates if I build a very small sample or a very bulky one. Therefore, in this case, we cannot deposit samples following standards for material testing, but we have more or less to create our own testing strategy, then to characterize the material, have the material properties that will be used then in the simulation to get the final shapes that we want. The last problem that we get in 3D printing of metals in general, and especially with aluminum, is thermal deformations. So of course, you can imagine we have a process where we deposit molten metal on top of a solid metal that then tries to shrink and creates both thermal stresses and thermal deformation of the substrate. In this case, you can see also by eyes the strong deformation that we have on very thin substrate that can be, in the case of 150 millimeter long substrate, up to 3.5 millimeter along the length of the deposition. But also we have a significant shrinkage from the sides, leading to 0.8 millimeter deformation on the width of the substrate. So now I was hoping to have the results of this testing now, but they are currently ongoing. So thank you very much.
Thank you. And if we have a look in the agenda, I think it's time for the questions and answers session. So let's have a look online. Maybe we should ask all the presenters to stand in front of the camera. Yes, otherwise, don't try to hide. I mean, this is. And Miriam, do you think you can move the camera a little bit? Okay, they can stay close. You can stand close together to show the audience how close we collaborate within FlexCrash, but otherwise, not standing behind me. And let's see.
Do I need
Good.
to move?
Okay, they have to. Yeah. Let's speak close together. Yeah, like friends. Okay, let's see if we have any online questions. Okay, let's see. I start with a question to Sergey. How will you test the performance of the reinforced specimen in the project?
Thank you for the question. In the project, we will have different strategies to characterize the behavior of this AVFF, these reinforced specimens. On one side, we'll have these different tests in terms of tension, compression, and also bending. So this way we will analyze which is the behavior of the specimens without and with these reinforced parts. And also we are developing these different tests, these advanced tests that you saw before, to test also those specimens in bending or maybe in tension to analyze the behavior of this AVFF and the fatigue conditions. And yeah, mainly we are also working on, when we will have more results, we will work on the development of new tests and new configurations to capture all of these different behaviors of these specimens with these reinforced parts. Yeah. Thank you.
Okay, let's see if we have any questions in the audience. Oh, we have one. You can just check if you press the button there.
I think it works. Yeah, perfect. Questions to Simon and Daniel regarding material modeling. Are you using user-defined materials, material cards, or classic LS-DYNA material cards that are modified in a certain way?
We're using LS-DYNA, but it's a own developed model that will be available within the FlexCrash project. So we have prepared test cases, input cards, so you can start testing it right away with preliminary data.
Okay, so you need a certain solver version for that, or is it available in all versions?
We can compile it for all versions if you have some requirements.
And it's this propagation of the Six Sigma curves are available directly in this material card, or are they available in the post-processing process?
They are available directly. You can say in the input card, you have all the necessary input data. So you have the standard deviation and the mean value are included in the data. So as a user, you can change it if you have new data.
Okay, thank you very much.
Yeah.
Thank you. I think I'll take a question for the chat. It's for Francesco. Are there challenges in the position specific to the LMD machine you are using, or are they generally related to the position of aluminium? I'm referring in particular to overheating.
So the main challenging that I showed today are related more to the deposition of aluminium, where we have this effect of overheating, depositing one layer above the other, and we have to control the parameters then basically each layer because we have different deposition conditions. LMD today, it's quite common to deposit steel, nickel-based alloys, and titanium alloys, and with these three types of aluminum alloy categories, let's say it's more relatively easy to produce 3D structures. In those cases, the main problems today are more related to material properties, defects during the deposition, or control of the thermal stresses and thermal deformations. But then we can achieve significantly higher quality. With aluminium still, we are trying to work on a feedback control system to improve the deposition quality. But as you can see now, today we're still having some big challenges, but we can then deposit some already useful structures.
Thank you. I think we have another question. This is very closely related to the previous one. It's also for you. Can you adapt the laser power in each deposit layer to prevent overheating? It's a lot about overheating here. So.
Yes, exactly. As I said before, we try to control the process parameters in different layers to have a more homogeneous deposition. However, one of the problem I said at the beginning, I went quite fast, is the laser interaction with aluminum alloys. Because when we have aluminum alloys in the solid state, the absorption of the laser is really low. So it's really hard to create the melt pool. But once the aluminum is in the molten state, then the absorption is quite high. Therefore, it's really hard with the stable laser power to have the temperature of the molten metal, or in the case, the molten aluminum, just above the melting temperature. We always try to create the melt pool, and as soon as we have the melt pool, then it goes to 1500 degrees or something like this. So as I said before, would be what we are trying to work on now is feedback control system to try to control the temperature of the deposition rather than working on the process parameters like the laser power itself.
Okay, thank you very much. And I think the next question, I think is for you, Daniel. It's about how does the current LS-DYNA probabilistic metallic card work versus other popular material models like crash film and for crash burners estimation?
Yeah, we will evaluate existing models and also models that are not implemented in Dyna and compare that with our model. So I will come back with an answer later.
Well, we have the first cliffhanger of today. Some question for the audience? Oh, we still have plenty of time. Well, otherwise, I have a question to you, Sergio. And I took a picture of your presentation. You compared two different aluminums of these extruded profiles, and you compare the center work of fracture. The one with the higher value have quite low spread compared to the other one. I think it was 4 times larger spread for the aluminum with a lower value. Why? Could you explain why?
Yes, the point is that it's a good question. The main point is that, you know, when we are preparing these different materials and especially directly from a component, in this case from extruded component, we have many defects and different microstructure and different behaviors in the material. In these results that you saw were first results just to see which one performs better. But the main idea is to use more specimens, increase the number of tested material, and see if we can reduce this scatter in the results of the material. But it can be related mainly to the different defects in the material mostly. So this is why we can see this quite huge scatter in the results. Yeah.
Okay, thank you very much. And now, Simon, it's your turn. Yeah, it's your turn. And it's a question here. Regarding the model, how does the model predict the quality of the created part? It takes inputs from simulation software related to casting defects.
So I am the one answering this. Yeah, I can see. I just need to read the question. Well, of course, we can grade this kind of crash worthiness in different ways. One popular one in the steel industry is for sure the crash index and the crash index decreasing rate, that you identify cracks after a certain intrusion. When does it start to crack? The critical intrusion, where we do start to get cracks in the component. Cracks are always detrimental to the performance, of course, because it behaves in a unexpected manner that you don't want in a very carefully engineered crash zone. So to quantitatively rate this crash worthiness, basically we can use this in the later crash testing when we do actual compression tests and 3-point bending. So identify with the high-speed cameras, for example, to see when cracks happen and when they happen in the low displacement curves. So I think that's the main.
Thank you. The audience, please, in the room here, we have still 7 minutes. We have a question.
One more question regarding Daniel. Regarding the thick shell elements. Our feedback from Dyna is typically they're not so happy when we're using them because thick shell elements are a little bit special. You mentioned before you used 2 thick shell elements over, so you layered them.
Yeah.
How you tie them together? Break contact or?
No, when we have 2 elements on top of each other, they are connected in the nodes, so they stick together. But what we can do is that for each layer, we can kill each layer if we would like to. So what we have observed from testing, for example, is the outer layers, they are more brittle, or you have more defects. So that means that we will basically kill that layer that will have 0 properties. So that will change the stiffness behavior of the component. But to answer on your question, we have a node, they are connected. 2 elements are connected by a common nodes. That's how we do it. Mm-hmm. But I've used thick shell elements for composites for a couple of years. By that, so I'm pretty used to making layered properties, and it works even if you have very uneven properties through the thickness. So we will test it more. So I will give an answer later on how robust it is.
Especially regarding normal shell elements. Solid elements are fine for certain ways, but in a full vehicle crash, solid elements are not so useful regarding time steps.
No.
So,
but I would say that with this fixed element, you can definitely keep bigger time step in comparison with the solid model. As the example here, where we need really to resolve this outer layer, then it's required another solution than a solid or a thin shell. It doesn't work with thin shells.
Okay, thank you.
Thanks. And now a question for Sergey here. The stiffness method is here applied at specimen level. Are you planning to use it on the component level?
Yes, nowadays we are developing the method, or we developed the method at specimen level. It works well for some materials, and we are planning, and in fact we are working with some companies to develop this method and apply it to big components. So in this way we can test directly the whole component and assess the fatigue behavior in these big components and compare directly between the specimens and the big components, and see which is the main difference, or if there are any difference between the different results. And we are working on that. So it's a good point. Yeah.
Thank you. Some questions here in the conference room. Other one, I have a question to Daniel and Simon. And if you remember the crash box, Sergey was showing the happy crash boxes, and you can see how they are folding. So the dominating stress to axiality, of course, plane strain. And if you look at the calibration of your fracture locus, you are using plane strain specimen. And you told us that the different properties if you compare the surface and the core and the skin layer. So my question, do you think it could be wise if you complement your testing with some kind of bending tests?
I move here. Yeah, I would say that's what we have realized, that for validation purpose, we need to have a bending case. But what we do now in the material testing is that we first test in using tensile tests with this skin on top of it, and then we remove the skin and test it also without this outer layer where we have smaller grain size. So then we get the properties both for basically the core material and the core material with the skin. But it needs to be validated in a bending test. Yeah, but just to add also about the model itself, why have we developed a new model? Yeah, one reason is that we need to have it microstructure dependent, and in the future we will, you can say, import the initial state from maybe a CFD analysis. So we have the pore density. We get the variation of that because now we test the material only with a certain amount of defects, a certain defect density, you can say. So when that will change, then you need this mapping. Yeah.
Thank you. And I think we have time for one more quick question. 1 minute left. But maybe we are satisfied. In that case, we will have a half an hour break and continue at 20 minutes to 11 and talk about crash simulation and FlexCrash demonstrator. So please have some coffee and we will return back in half an hour. Thank you. Time for the second half of the first session. And I will now introduce Christian Kusberg from Virtual Vehicle Research. And he will give a presentation about crash simulation from advanced material models to virtual testing. So please, Christian.
Very much for this kind introduction. So I will go forward from my previous speakers, try to give you a short overview of our daily work, starting from material modeling up to virtual testing, virtual validation, and hopefully in the end, virtual homologation. But first, start in the real world. So this is our daily work, let's say, crash testing, different cars, different scenarios. And now a question for you. What do you think cost one of these tests, one scenario with one car in the real world? Any suggestions? 100,000, 500,000? So one of these tests costs up to 1 million euro for one scenario, for one car. And car manufacturer all over the world has to fulfill a huge amount of different tests, different approvals, and different certifications. So when you want to bring a new car to market, you have to pay a lot of money just for testing. And that's what we are working on, because we want to try to reduce these real tests in the development process and try to get a virtual validation, a virtual testing, and in the end, a virtual homologation of the whole car. So why we are not going fully virtual? Actually, it's worked. We can simulate, we can predict behavior of different materials, of different components, up to full vehicle simulations and full vehicle behavior in different crash scenarios. But the first starting point is what Simon and Daniel mentioned before in her presentation. We have to understand the materials. So we have to know what the material is doing in certain load cases, in certain crash scenarios. So we are typically starting with Young's modulus, with density, with the base material properties. Then we are adding some stress strain curves, some plasticity. So that's the base work, for example, for metals and for different alloys. It's quite easy. The next step would be to add some strain rates. Different materials have different strain rates, so we have to add them to predict the crash behavior in different load cases. The next step would be failure and damage from the material and also from connection points. So connection between different materials, different connection technologies. There are up to thousands of different connection points in a virtual simulation. And you have to predict every single point correctly to predict the crash behavior and the energy absorption correct. And the last step that we are working actually and also in FlexCrash are these production-related properties. Especially for high-pressure die casting parts, the production process influences massively the material properties. And we have to predict these material properties and the behavior of these properties in a certain crash or a crash scenario. So these last row here with these production-related properties, this is the actually ongoing research work since 5-6 years. We are dealing with this mapping process to bring this work from the university, the research programs of the universities, to fill this gap up to the industry and to bring it in a full vehicle simulation and a virtual development process for new productions and for new cars. So how are we doing that? We are starting at the base level, coupon level testing for characterization. Some of you know that. You test some coupon levels, you get some data from that. You use that data to validate your material models. You fix some issues. In the end, you have a material card you can simulate on component level. So with this component level, we are going in more complex testing situations. We validate our material cards. When we have some issues with the material cards, we can go a step back to the material model calibration, modify in certain ways, use another material card use other methodologies, other element formulations, and try to modify our simulation purpose and get a new model on the component level. And after we have fixed all these issues, we can use that material card in a full vehicle validation. In a full vehicle validation, the complexity is increasing quite high. So we are reducing tests and we're using even more simulation for that. And what we are trying to do is to enhance the forecast quality with every step to predict the behavior of the full vehicle in different crash situations, crash scenarios. A short drawback to where is simulation coming from. So in the 80s, we are simulating quite handsome models with about 500 elements just to get a feeling of how these structures are working in different situations. Actually, we are going up to, this is from year 2014, 4.5 million elements. Here we can see in Volvo XC90 generation 1 and generation 2 with element numbers of about 300,000 in year 2002, up to 10 million elements in 2015. Actually, we are going up to 16 million elements in a simulation model. Typical run times for these full vehicle crash simulations are here given with 30 hours. 30 hours is not so good, let's say that way. Normally, we're trying to reach a simulation in 12 hours, so we can modify every day a new scenario or a new design of different components. And typically, we are using for these full elements, full vehicle simulation, shell elements from 3 to 10 millimeters. But for these high pressure die casting components, we are going to typically solid elements with element lengths about 3, perhaps sometimes 2.5 millimeters to reach that the given time step from our project partners. So what are the requirements for these full vehicle simulations? It's not only the material card we are working on, we also have some other issues in the full vehicle simulation. We have airbag deployments, we have inflated tires, what has to be simulated correctly. We have connection failure. I said before, more than 1,000 connection points in a car, which has to be predicted and to give the or to predict the right energy absorption and the right deformation of these crash areas. Shell barriers are even better, getting better and better. The development of that is a huge point, especially when it comes to compatibility of different cars. And when you see here this small overlap crash from this Volvo XC90, was it captured there? What failure do we implement it in such a simulation? So failure in all joints and all materials. The welding connections are implemented with different failure models and methodologies, and also these detailed wheel models for this crash scenario is really crucial for the energy absorption and the behavior of the whole car during this quite critical and quite difficult test to fulfill for the car manufacturer. And yeah, main point is avoiding CPU time regarding element formulations, regarding small elements in high pressure die casting parts. So that's a real crucial part. I said before with a colleague, this rim can be modeled with hexagonal elements in solid elements. So it takes us about 2 weeks to mesh one of these wheels. Or you can mesh them with triangulars, and this takes us about 2 days for the same wheel. And we want to have the same, or we hope that the different methodologies, how to mesh it, give us the same results in the end. So that's, we can get a benefit out of easier meshing, but the results in the end should be the same. So that's what a physical test compared to a simulation test could look like. It's a quite easy scenario, rigid wall scenario that works quite well. We are dealing with that since several years. We can predict the behavior. We can modify design in front-end crash structure. We can lightweight design. We can optimize structures for these given scenarios. But what we are also do in FlexCrash and in other projects is to come from this quite defined scenario to new crash scenarios. So this is also one point in FlexCrash. We want to define new crash scenarios for future mobility. And this could be, for example, turning accidents or these real world testing. So we have two different cars moving together and crashing. So it's quite difficult to really test that on a test bench because when you have two moving cars, it has to be defined exactly where they hit together. In the simulation, it's quite easy. And when we are predictive enough for that, then we can show or we can virtually test, virtually validate, and in the end we can virtually homologate cars and are not even more restricted to physical tests in the real world. So I should summarize what are the requirements. We need credible and reliable models. We need a standardized procedure how to document these results in different solvers, in different material cards. Everyone has different internal papers how to model such things, and that has to be standardized. What are the benefits? Faster production development, cost improvement, higher safety standards when all of these standards are standardized. What do we need for virtual validation? It should replace the real world testing, not all, but most of it, especially when it comes to full vehicle simulations. And what are the safety level improvements? So we can simulate various situations. We can simulate whatever the government, whatever US NCAP, Euro NCAP is asking for, and you can be sure that the cars will be safer with this virtual testing and virtual validation because it tested more realistic scenarios compared to the actual quite restricted and quite well-defined crash scenarios. And the virtual homologation, I think, for our company is the right way to develop and to manufacture new car and new car new designs and new cars, lighter cars, and to have it to have more safety features and safer cars in the future for all of us. So thank you for your attention, and I'm waiting for your questions afterwards.
Thank you very much. And I would now welcome the second speaker. You can go direct. That is Andone Aguirre from Gestamp, and he will talk about the FlexCrash demonstrator and adaptive crash tolerant structure.
That's right. Yeah. I don't know if it's working properly. Yes. Okay. So thank you, Jürgen, for this introduction. Also, Christian, for your presentation. I think it was very interesting, and it matches my presentation matches perfectly right after. So today I am going to introduce FlexCrash demonstrator. So I'm going to start first defining which are the initial requirements, no, and the boundary conditions that we had to fulfill when we started to define this demonstrator. We'll go through the steps that we have followed during this design. And finally, I will show the status, no, the current status of this demonstrator. Going to start with a small spoiler, just to say that the demonstrator is not completely defined yet, so we are still working on it, because the aim is to introduce or to integrate as many outputs as possible from the project. So we will take into account topics in additive manufacturing, as Francesco explained before, or in material modeling, as our colleagues and Simon explained before. So we are still working on it. Okay, so what is the motivation, no, and the requirements for this demonstrator? So the idea to define a front structure, so a crash-tolerant structure that could absorb as much energy as possible in a frontal crash, so that the injuries on the occupants are minimized. So for this purpose, as always, when we design for crash, there are many legal requirements that we need to fulfill. So we need to, of course, reduce the injuries on the occupants, but not only on the occupants, also in the pedestrian, in case of a huge car crash scenario. Also, we need to take into account compatibility issues, because you can see that the traffic now is more and more heterogeneous. We have big SUVs, small city cars at the same time in the road, so heavy battery EVs. Soon we will have automated vehicles and so on. So we also need to take care not only about the occupants of the car we are designing for, but also for the occupants of the other cars. So there are many engineering parameters that we need to take into account, but also, of course, very important also economic and ecological factors, because at the end of the day, we want to promote, to industrialize a solution. It has to be affordable and of course also sustainable. So these are general requirements that we need to fulfill when we design any crash structure. But on top of this, we have some particular requirements for this project that we can see on the right side in blue. So the first one is that the concept, the demonstrator, has to be full aluminum. So it was one requirements of this call. Another one, another objective for us was to perform the virtual validation, not only in component level, but also in full vehicle models. So this is another requirement. And finally, since this FlexCrash project is a project funded by, we also wanted to create some links with European projects to create some synergies for the present and also for the future. So we have seen the motivation, no, and the requirements. So then we had to define the tools, no? How, what are we going to use to define this demonstrator? So on the left hand, we can see the full crash model that we are using in this project. So it's the Stamp GLAB model. It's a battery EV that represents a CD segment car. You can see here more or less 4.5 millimeters length and 1,800 kilograms of weight. And the other step was, okay, we have the model. What crash scenario are we going to design for, or at least to start with, no? And in this case, we started with the Euro NCAP MPDB crash scenario. So we can see here that it's a crash scenario with an overlap of 50% between the barrier and the car. We have here also the speeds of the car and the barrier that are 50 kilometers per hour, the barrier 1,400 kilograms. And in this case, we can see that the crash angle is 0 degrees. So the axis of the car and the barrier are parallel.
So then the next step was to say, okay, which are the parameters that we are going to look at in order to determine if the design is good or not, if it's working or not. So the first one is, as usually, the kinematic, the deformation. So it's a visual verification that the structure has a good deformation, because usually if the kinematic, if the deformation is not good, the structure will not absorb enough energy, and hence we will have big intrusions into the dust panel. So the dust panel is the wall that separates the engine zone from the safety cage. So what we want is always to reduce the intrusions here, because it's directly linked with the injuries on the occupants. So these are the important parameters, but not only, also the decelerations, because perhaps the dust panel intrusions are not so high, so we don't have a big crash between the occupant and the structure. But also the decelerations are important, because otherwise, if we have high decelerations, perhaps we can have internal injuries in the occupants. So there are some of the parameters that we have selected in order to define or to work on this demonstrator. Okay, so we have the requirements, we have the tools. Let's start with the definition of the demonstrator. So the first input that we had was this Salema part, a die casting part in aluminum that we can see here. So the idea was to include this in our demonstrator. So the first step was to put it into our GLab model and see how it fits in the environment. So we saw that, as we could expect, there were many modifications to be done around, because this part was not designed for this vehicle. So we had to modify several parts around this green part. And once this was done, we said, okay, we need a full aluminum. Let's in aluminum, the ones that we can see here, in order to complete the demonstrator. So we decided, or we designed this main rail, the main front rail, the front bumper as well, and the secondary rail that we can see here. So we put together, and we saw that it was not working so well. It was not working so well. This is something we could expect, because usually when you design for crash, if in the first iteration you have a good performance, is that you have been quite lucky. So unfortunately, we weren't so lucky. We had to iterate a bit. So we saw here, this is the FlexCrash design. So we saw that we weren't compressing the rail, so we can see that it's bending on the rear side, so we don't absorb enough energy. This is what we can see here in the lower part. So the blue curve is this FlexCrash first design, and our target was the black curve. So as a consequence of this, we could see that the intrusions into the dust panel were very, very high. So this was not acceptable. So afterwards, we did some iterations. So as we usually do, we modified the geometry, thickness, sections, and so on. We test, we do some loops, in order to improve the performance. And finally, we managed to get a concept that it's working much better than the first iteration, as we can see here. So we have a better compression of the extruded profile, and as a consequence, the dust panel intrusions are much lower than previously. So this was a step, or a status that we got after several iterations, but As I said, we are still working on the demonstrator. We are now in the optimization phase. So we are working, of course, in full model level, but also in component level, because what we saw is that this Salema part, it was too stiff for our VLAB architecture. So at some point, when the extruded profile was compressed, all the front unit was coming into the safety case. So what we are trying is to somehow tailor the stiffness of this component in order to have a better compression of the complete front rail, so the extruded profile and also the casted part. So this is our work we are doing. But not only, on top of this, we are also exploring how we can integrate this ABFF, as Francesco explained before. So here we are also analyzing different patterns and optimizing the geometries and so on, so that eventually could use the thickness of the substrate of the preformed part while introducing these patterns and finally reducing the complete weight of the complete design without having a worse performance. So up to now we have seen what happens in a standard situation, let's say in the EuronCap MPDB, but what happens now when the crash is not a standard situation. So as Christian already mentioned, colleague Sarita will explain after also, one of the pillars of this project is to identify and to anticipate to future crash scenarios. So what happens with our demonstrator when the crash is not the standard protocol, but it's slightly different. And here we can see that when we introduce a small modification in the crash condition, in this case, we, instead of having a 0-degree impact angle, we have 15 degrees of impact angle. We can see that the behavior of the front unit is completely different. So we have not very the quality of the video, but we see that the kinematic has changed for the front unit, and as a consequence, we have more intrusions into the dust panel. So this is something we are also facing now, how we can have a more robust design, and this is why we are now trying to explore also how we can integrate an active our demonstrator, so that the active system of the passive structure will somehow complement each other, and we will have a more robust design, not only for standard crash scenarios, but also for not standard situations. So just to sum up, so finally, the demonstrator, it will have several components. It will have this die-casted part. We will see if it is exactly like this, or we will do some post operations on it. We will also have some extruded profiles to complete this structure. We will have some additive manufacturing features in order to optimize the passive structure. And finally, we are exploring how to integrate this active system in order to have a more robust crash tolerant structure, not only for current crash scenarios, but also for future crash scenarios. So it was all for me.
Thank you for the short introduction. My name is Sarita and I'm from CREMS. I'm going to introduce the FlexCrash platform. So the idea behind developing the platform is developers, regulators, or other interested parties can play around with the vehicles. They can study the live interaction of the human drivers and the autonomous vehicles so that we can identify the critical scenarios so that we can avoid the critical scenarios in the future. And the platform implements an online turn-based multiplayer game. So it is a web-based application which uses REST API so that we can integrate the autonomous vehicles easily with the features using different technologies and also the scaling. So scaling so that we can create many number of scenarios. We can simulate many scenarios with many autonomous vehicles as well as with the human drivers. So this is the idea behind the platform. So some of the goals that I have in the presentation is, at first I will introduce the platform so that we can explore the testings. We can create the scenarios. We can create human drivers vehicles as well as autonomous vehicles so that we are able to drive the vehicles using some control parameters. So that means we are going to test whether the platform is implemented in a right way and it does the things using the right commands, so right things in a right way. So we want to test it so that also at the same time we'll have a look on the usability test. I mean, you as the audience will provide us the feedback on the usability on the platform. That means, is it the platform user friendly? Can you easily use the platform? So at last, then I would like to collect your feedback. So the first things first, scenarios. So how to create the scenarios? We need to use some template, which is for now there is a defined template. Static definition of the driving scenarios is in the template. So there are some roads, 2-lane roads. I will show you in a later slide. And users cannot update the template, neither can add new template. So it's there is a template provided which includes only road networks in a common road format. So there are 2 lanes, there is a common road, and the vehicles would be driving in both directions. And after that, once we have this template, once we create our scenario using the provided template, then we have to drive the vehicles. So how long we want to drive the vehicles, this is defined while creating a scenario. So we need to define some time in seconds so that we have some simulation steps depending on the time we provide while creating our scenario. So that we involve 1 or more drivers or 1 or more autonomous vehicles. That means we have human drivers and autonomous vehicles in the scenarios. So currently we have only 1 AV implemented. And so we need to have the vehicles and we need to have the target of the vehicle. So where does a vehicle want to reach? 2 lanes, so we need to keep vehicles in both lanes so that they want to reach in the opposite direction. So we have some positions, some rotations, and the speed. From an initial state, we can even control these parameters so that we have the vehicles which have the destination target position, and we want to drive the vehicles without colliding, so staying within the road, so driving off the road. So then the platform maintains the state of the driving scenarios and monitors their execution. So AVs drive by planning their driving trajectories and submitting their next planned state. So there are several commands or the buttons we can use. So how the planning is done. There are, for example, target speed. We can use higher or lower speed, so we can reduce, accelerate or deaccelerate the speeds. And we can also move, click some button, use the feature so that we can also set the vehicles move to the right or to the left. So we can then use the time, actuation time, that is the time to reach the target. Using several parameters, the platform computes the trajectories and lets user change various parameters. So it will be shown in the demonstration later. And yeah, so drivers can also plan more than one step in the future using the planning horizon. So once we create a scenario and drive the vehicles in the scenario, then once they are done, all of the simulation steps are done, then we can even, these scenarios will be closed once the driving is done, then we can even download the simulated data as a file, as an XML file. So it would enable for the data analysis and would be input to the future. So this is what is done so far in the platform. And regarding the scenarios, there are grouped in different types. For example, the scenarios want by the users. So users can create a scenario, but still if a user create a scenario, then it's not automatically, it is also the user join the scenario. So the user can join many scenarios. So for example, 1, 2, 3, 4, or many more. And these can be other group of scenarios in which the user is a driver, or that the user had joined in several scenarios. So there are different groups of scenarios, so to say. And so here there is you can see there is a prototype in the link, which is hosted in INC. So in the platform, we need to at first log in as a user, as audience. You can use users provided in the chat. So there will be some users, a list of users provided in chat, and using one of the user, for example, in the file that is provided in the chat, there are username, email, and password. Please use email and password to log into the platform. So first of all, you log in into the platform and then you create a scenario. Or if there is already an existing scenario, then you can also join the scenario. And yeah, so as I said, if you create a new scenario, then it's not automatically you are in the scenario. To be assigned to one of the vehicle, you need to join the scenario so that you are assigned to a vehicle in a scenario. That means now you are able to control the vehicle. So that means you can accelerate the vehicle, you can deaccelerate the vehicle, you can go to the left or right, you can change the time and so on. There are several features, the commands, which you can click, and in a click you can control using different vehicle parameters, you can control the vehicle. So to drive two vehicles in the scenario, at least two of you have to join in the same scenario so that two of you are controlling two vehicles in two lanes in different directions. So please use the usernames provided, and once you set the parameters, then you can drive. So you join the scenario and then you can drive the vehicles, and you can set the parameters so that you can see there is calculation in the trajectories, and you can see if the vehicle is going to collide. So there is an example, the demonstration of the video. So this is, you can see, so this is the prototype. We have running prototype. If possible, then I'll try to share the video after this next slides. So using the platform, then please log in using the email and the password provided in the chat. and try to create a scenario there. So set the time to 3 seconds so that it will be 40 simulation steps. And so once you create the scenario using the template, so click on the template so that you can see there is a purple border on the template, so that click on the create and you can see you can assign the time. And even there is a button add vehicle. So click on the button add vehicle so that you can add 2 vehicles in the 2 lanes. So the circle is the vehicle and the rectangle there is the destination you want to go. So the driver or the vehicle want to reach some destination. So this is how you put 2 vehicles in 2 lanes, and you can still see there are 2 arrows in the template. So the arrow means it is pointing, so you can drive in that direction. So arrow should be the initial state, and your destination, the circle should be in the initial state in front of the arrow, and the other box, the rectangle, should be in the destination at the end of the lane. So keep the 2 vehicles in 2 lanes. If you click on the circle, for example, on the green circle, then there will be a window pop up. So you can control the speed of the vehicle. So sorry, everything was shown in the video, but yeah. So if you are playing around in the platform, then this is how we can create a scenario and drive the vehicles. Maybe I will log in and I will say. Yeah.
What do you think if we try to solve these technical things and then we start with the discussion? And you have 5 minutes. We take 10 minutes of questions and answer and then end with 5 minutes with your demonstration. Do you think that's
Okay? Yeah. So it's then this is how you create the scenario, and then so once you create the scenario, providing 3 seconds, adding the vehicles, you create the scenario, and then after that, in the next step, join the scenario. So task 3, join the scenario and try different parameters in there and try to crash. So try to drive the vehicles. 2 of the users, please join the same scenario and try to drive the vehicles by setting the different parameters and try to crash. And the 4th task is, so it's you can also make a group so that many of you can join the same scenario and try to drive many vehicles. So maybe 1 vehicle is in front and the other vehicle is behind in 2 lanes. So you can, 8 users can join the same scenario and 8 vehicles can be simulated in the provided template. So then I hope once you do these 4 tasks, then you will find out some issues and which issues did you find. So how critical are they? Please take some notes and if possible, then please provide some suggestions for the improvement. So if there is anything missing, then we need to get in front of the review. So please, provide your feedback in the Google form. So there, please use the Google form and provide your feedback in there. Also, even you can send you an email if you have any other issues and questions. So I'll be more than happy. We'll be more than happy if you get your feedback so that we can improve it in the future. So thank you very much for listening the presentations. Thank you.
Thank you very much. I have one suggestion for improvement. Instead of having this 91, the address, put up a QR code so the people can take a photo directly. That's an easy. Okay, I think I will ask the first two speakers to come up here, and then let's see if we have. Yeah, we have plenty of questions in the chat, so let's see. We start with you, Christian, here. Would it be possible to replace all physical testing by virtual testing and validation?
Technically, it would be possible, but we are not supposed to do that way because we need some physical tests, especially for the material modeling. After this validation phase, I think we can skip a lot of the physical tests with on component level and especially on full vehicle level.
And I have a follow-up question as well. One question for you. What are the biggest challenges on the way on to virtual validation?
I think the biggest challenge would be the standardization of the different solver types we're using, at different material cards, material element formulations. So to get it all together, to get it comparable between different companies, and to have an overview and the documentation of the models. So that would be the most critical point, to have all on the same page in the end, and to have an virtual homologation possible for future crash scenarios, for future car generations. So that's would be the most critical point.
Thank you. And for Andon, I have a question here. What is the overall weight reduction of FlexCrash demonstrator versus with the compared to a full steel structure? With respect to a full steel structure.
Yeah, this is something we are still working on because yeah, it will depend on all the ABFF that we are able to introduce, and also the weight of the active system. So unfortunately, I don't have the answer yet, but it's a good opportunity to promote the results that we will get in the upcoming months. Yeah. So I would say that everybody should stay tuned to this project.
Thank you. Some questions from the room here. Let's see if we have someone. Don, are you preparing a question? Yeah.
You mentioned, Andoni, that it was designed, this component was designed for another vehicle. Was it a vehicle with the same weight as you asked G-Lab?
Yeah, I don't have the details of the vehicle that was considered in this project. I don't know even if there was a vehicle, or it was just based on benchmark, because as long as I know, the scope of the project was different, was more related with critical materials and so on. We will have more details afterwards, because the Salema project will be also presented later on. But what is clear is that it was not adapted for this CD segment that we have G-Lab, because it was a big part, considering that we were not integrating the shock towers. On shock towers, we can have big parts in die-casted aluminum in the front unit, but in this case, it was too big.
And it was also not designed for crash purpose. So it was for durability designed, not for crash purpose. And it was one of the actual working points we are trying to get it used for crash scenarios, because it was way too stiff and it doesn't absorb any energy.
Thank you. Then I have a question myself to maybe both of you. You had a slide showing how you could increase the capacity when it comes to modeling. It increased more or less exponentially. And I mean, we have some young people here inside, and let's say within 5 years, then they're becoming engineers. What could they expect? What is possible within 5 years? It's a tricky question.
It's a tricky question, especially regarding model size, and also a huge point actually is AI capacity for modeling and for virtual validation. So how can AI, MI influence future car generations, and how can they help us to improve the crash safety, improve lightweighting? I think the elements number is actually not improving like that from the last 20 to 30 years, because capacities on high performance computers are limited. But the next step could be the integration of AI, MI in this development process, and that could lead to an a massive decrease in development times and also in cost.
Thank you. I have no more questions in the chat. Some other question for the audience? Otherwise, before we have the short video of the platform, I have a question about, it's a gender-related question about, you see, in the crash test, you have some dummies fully instrumented. And what I heard, you make most of the kind of simulations and tests, and everything is based on the male anatomy, not the female. Like, of course, it makes sense because a lot more accidents, and because we overestimate our skills, which becomes even worse after 50 years old. But are you trying to simulate what happens if you put in a dummy with a female anatomy instead of just using as? Yeah, you understand the question?
Also an interesting research topic actually, because there was the first female dummy introduced, I think 1 year ago. We're also dealing with female dummies on the virtual world. But there is, for women in the car, it's more critical than for men in the car. So occupant safety for women is not related to design and to safety issues. There is I know only one car manufacturer who is dealing with different types of people sitting in a car regarding the position of the seat. So when they inject the airbag, it's had two different stages regarding the position of the seats. They think when there is the position part backwards in the car, then it's a heavier man, a bigger man. So they has to deploy the full airbag. When the position of the seat is more in the front of the car, then they have to deploy only one stage, because then it's lighter people, it's a smaller woman expected, and when the airbag will be fully deployed, then it doesn't work that well. But yeah, woman in the car is not the best protected people in a car actually.
We have a homework to do then. Yeah. Okay, then thank you very much. I think it's time to have this short video. We have a few minutes here, so please.
Finally, we have the video here. So here it's trying to log in. So you can see there are several scenarios, and a new scenario is created. Two vehicles are added in here. The speed can be controlled like this. For the green vehicle, which has human driver, this is the starting point, and that is the destination. Similarly, for the another vehicle, which is AV, and the speed is controlled, and 5 seconds is there. So that once the scenario is complete generated, it is joined, and now can add the different parameters you want to decelerate and want to drive less, and so on. So it's computing and calculating the trajectories. So here, so the parameters are submitted, and once the other user also submit the similar parameters, then they can drive. So you can see here it is updated And the steps are done there. They are active, they are pending, so it is automatically, the simulation steps are updated, so you can drive the cars. So at that time, please do not refresh the page. It is automatically updating the steps, so we can see there are states of several simulation steps are changing, and even now you can see the parameters which are used to control the vehicles are changed, and it is automatically refreshing the page and updating the states. So it was 5 seconds. So in this simulation, there will be 50 simulation steps. And it is, see the steps here, they are generating and they are becoming active. So once it reaches to 50 steps, then we can drive the cars. So it takes some time. So there are 50 steps. So the right arrow, you can also click on the right arrow so you can see whether they crash. So you can see here export as, so data, the simulation data can be is saved in database in the backend. So we can use this data. We can easily download the data and use it for the future data analysis. So that's it, how it works and how the simulation is done in the platform. Thank you.
Thank you very much. And let's go back to the agenda again. And I realize it's time for me to leave the arena here. But now it's time to introduce the next chairman for session 2, Daniel Casellas. And we now here we listen to a number of presentations about related projects to FlexCrash. So please, Daniel.
Okay. Thanks, Jürgen, for sharing very actively and very nicely this first session of this FlexCrash conference. Now it's time for the second part of the second session of this conference. It's time to learn more about what is going on in European projects about materials for safer and lighter vehicles. My name is Daniel Casellas. I am a scientific director at the EURECAT, Technological Center in Catalonia, and I'm also a adjunct professor here in Luleå University. So what we're gonna do in the coming 1 hour, more or less, is listen and know about three projects. We call it our FlexCrash sister projects. Is the Salient project, the Salema project, and the Flamingo. Both, all of three projects are related to materials for sustainable and safer vehicles. In every project description, we will have a first introduction about the project, aim and concept, and following with a technical presentation about some of the relevant part of that project. So we will start with the Salient project. It's time for Vanessa Ventosinos, researcher from the Automotive Technological Center of Galicia, to explain what is the Salient project. So Vanessa is involved.
Hello, everyone. Can you hear me?
Yes, we can hear you.
Great.
So
let me share my screen.
Put on presentation mode, please.
Yeah, sure. Now. It takes, some seconds
Vanessa,
of delay.
go ahead.
Perfect. So first of all, thank you very much for the kind invitation to present the sister project, Salient. So as you probably know, like a couple of years ago, the Commission, the European Commission, detected some challenges regarding the safety. And in fact, they launched a call to ask for new projects to address those challenges. So these are extracts from the topic, from the call. So they detected that the new structural concepts needs to be designed from a circular approach. Because it's it's always important, but in mixed light material structures, it's a particularly high challenge. It's very challenging to go for this circular approach in terms of recycling and even refurbishment and reuse. They also ask or remark that lighter vehicles, which are needed to reduce the energy consumption, also mean an intrinsic reduction of safety when they collide with a heavier counterpart. So we should go for lighter vehicles, but we should also address this lower safety due to that. They detected as well that we are going to face a mixed traffic situation quite soon, where automated and semi-automated vehicles has to live along with manual-driven vehicles and all kind of unprotected road users. So it's also challenging. They have to take into account each other in order to have an overall safety environment. And also that the vehicle structures are optimized only for the exact tests that are in the regulation and in Euro NCAP tests. So they are not optimized for real crash, let's say, only for those that are already standardized. So it's also something that we should take into account for the new developments. So in this environment, Silent was born. Our intention is to face those challenges through an innovative front-end structure. We have focused our efforts in the front-end structure because it's a very representative component for safety in cars. So we go for a circular, modular, and eco-design front-end structure that is made for dismantling and end-of-life options. It should be also lighter, of course. For that, we use new multi-material design with high performance strength and crash worthiness. It has to be safer. And to do so, we work with both an baseline front-end structure that it's safer by design, but also including adaptive concepts, which leads to the smarter front-end structure. So I'm going in further details later on, but the thing is that this front-end structure is able to adapt itself to a real crash scenario. So we are 12 partners involved in this project. It's led by CITAGA's coordinators, but we are a lot of partners involved to these ambitious goals. It starts in September 2022, and we have a general budget of 4 million to achieve our objectives. So the main objective, as I mentioned, is to have a new front-end structure with 3 main objectives in mind. First, it has to be lightweight by at least 42%. It's quite ambitious. If you compare with the baseline, which is a traditional steel-based front-end structure, our baseline was a Fiat Panda, for you to know. Also, we have to check its safety, that it fulfills all the crash standards, but not only that, also additional crash angles, and to design it for circularity. So easy dismantling, as I mentioned before, and reuse and recycling. So to do so, we consider advanced materials such as aluminium, hybrid structures, and thermoplastic reinforced with carbon fiber parts, so made of tapes. That include shape memory alloys in order to be active. So considering those innovative materials, this is like the workflow that we have followed to reach a design. First of all, we perform a constraint analysis. So the new materials, of course, have limits in terms of manufacturability, in terms of design freedom, and also in the potential crash behavior. It's not the same, the collapse of a thermoplastic fiber reinforced component than an aluminum one, and of course, let alone a steel one. So we have to be very careful analyzing such constraints and to design something that is feasible, that is manufacturable at the end. On parallel, we also perform eco-design assessment on the different versions of the design, on the different options for the front-end structure. I'm going to explain further details later on that. And or with this first assessment, this first analysis, we design different options for the front-end structure. And we perform a Chi analysis just to check through simulation and that we fulfill all the requirements with different crash scenarios. And we analyze that at component level, but also at full vehicle level, just to be sure that there is an impact in the whole structure, in the whole vehicle. So it was already mentioned that you cannot expect to succeed at the first loop, at the first design. It's an iterative process. So you first have this first evaluation through simulation, and then detect all the failures or the optimization are needed, and then you have to redesign that once again, and like several loops after that, you get your final design. So, as I mentioned, the first step for an eco-design is, the assessment of the different options that you have for a given product. So we take into account some critical key parameters to weight or to assess and compare different designs. The first one, of course, because it's one of the main goals of the project, is weight saving. It's related with the carbon footprint, because even for electric vehicles, it's related with energy consumption and also material consumption, of course. We should consider also recyclability, if it's easy recyclable or not. With a full steel solution, recyclability in general is not so difficult, let's say, but we are talking about a scenario with mixed materials, so it's quite difficult to assess that. Of course, it's not the same to recycle aluminum, which is quite easy to be fair, than, for example, thermoplastic materials reinforced with carbon fiber, of course. Related with this recyclability issue, we have the assembly-disassembly, but not only for recyclability, it's also important for repairability, to increase the lifespan of the product and to allow refurbishment. Also related with the carbon footprint is the number of reference saved. So the lower the number of parts, in general, the lower the energy is required to produce the final function. So it's also something that we have considered, and also it's cost effective. That it's also, we should consider that we are working for high volume production cars. So the cost, it's something that we should always consider in a new design, even talking about eco-design. In this line, we have also assessed the assembly line compatibility. If you have to completely change your assembly line, not only it has a tax on the energy that you are consuming, but also on cost effectiveness of the solution. So we have considered all those key parameters to weight or to score different options. And finally, we reach a final version of the front-end structure that has a 52% of weight saving. It's not the final one. I mean, we are now still on the optimizing phase to reach the best crash performances that we can. So for sure, in the following months, we maybe have to add some reinforcement or some new systems to that well, in a way, they are going to add some weight on the final solution. But well, we are very happy with this first and preliminary result that left room to achieve our ambitious goal of 42% of saving. But from now, we are talking about a quite traditional solution, let's say. It's still a front-end structure that reacts to different crash, but without changing its behavior adapted to different crash scenarios. So where is the smart consideration here in Salient? Well, to this new front-end structure, we are going to add active solutions that are able to adapt the front-end structure to an imminent crash. It means that the ADAS systems are going to detect a crash that is about to happen, including the speed, the angle crash that it's expected to occur, and so on. And then those active systems are going to take place to adapt the front-end structure to this very specific crash. To do so, we have the shape memory alloys included in the crash box, for example, that changes the stiffness of the crash box according to such angle. We are going also to include active tapes that are able to bend the struts a bit, not too much, but a little bit, in order to allow that the front-end structure face as well as possible the crash angle, in order to promote a great collapse of the crash box and the best energy absorption as possible. And also we are going to include inflatable areas in the bumper. That not only is going to change the angle, the crash angle of the bumper with the object that we are going to collide, but also includes some internal pressure that it's able to absorb much more energy than the bumper itself. So we are now in this phase of including the active systems and optimize all the front-end structure with that. Our expectation for the projects then, if we succeed at that, is to have not only a scientific impact through patents and training course modules in order to go beyond the state of the art, of the current state of the art, but also we expect to have economic impact in terms of employment thanks to this innovation. And of course, social impact, not only talking about environmental performances and carbon footprint, but also in terms of reduction of the overall fatalities during the accidents. So I think it's all. Thank you very much for your attention. And this is like a very quick overview of Salient project.
Thanks, Vanessa, for this nice, interesting introduction to the Salient project. Now we move to the next speaker. Also for the Salient project, it's Patrick Nossel. He's a researcher at Fraunhofer IWU, and Patrick will talk about crush structures in fiber composite construction for sustainable mobility. So, Patrick, are you online?
I'm online. I hope you can hear me and see
Yes.
me.
Yes, we can
And
hear you well.
I will share now my presentation with you.
Perfect.
Everything is fine. Can I start? Yes?
Yes, please start.
Okay, so I'd like to welcome you all. My name is Patrick Nossel, and I am representing the Fraunhofer Institute for Machine Tools and Forming Technology, IWU, specifically the Department Systems of and Technologies for Textile Structures, STEX. And with the topic crash structures in fiber composite construction for sustainable mobility, I'd like to give you some insights into relevant results in internal studies and also in the projects COSAL and the EU project Salient, in which I have had the opportunity to contribute to. So firstly, I like to address the key areas of lightweight construction, electromobility, and circular economy, which will be essential for the transformation process in the next years for the automotive sector. In particular, in my presentation, I will focus on the reuse of passive safety structures as schematically illustrated here in this picture below. For this purpose, we need a right material with the required performance. I will focus here on carbon fiber reinforced plastics, CFRP, which shows excellent specific properties such as specific energy absorption and fatigue strength compared to other materials. You can see it here in these diagrams above. Using CFRP materials, we even speak of durability for continuous operation, making it ideal for reuse applications in the circular economy. So let me start with the results of the Fraunhofer internal study on fiber composite compatible crash mechanism. In recent years, I conducted this study and optimized a specific crash mechanism, the inversion crash mechanism of a CFRP crash tube, as seen on the top picture and schematically here on the left below. This crash mechanism has many advantages. Significantly higher specific energy absorption values compared to crushing of CFRP and the aluminum buckling. Well, we can say that compared to aluminum, we were able to absorb over 4 times more energy, as shown here in this diagram below. So 4 times more energy with CFRP compared to aluminum. And we can say that we can build such a crash absorbers 4 times lighter with CFRP than with aluminum with the same energy absorption level. Now I like to present you some of the COSAL project results. The COSAL project was founded by the German Federal Ministry of Education and Research. COSAL stands for Reusable Open Source Design Kit for Electrically Powered Pool Vehicles. Let me start with the goals for our institute in this project. Well, in general, we want to have a more eco-friendly mobility by means of circular economy, new long-lasting vehicle platforms. So that the main goals for our institute in the COSAL project were reuse and remanufacturing designs concepts for a durable sill structure, The cell structure should be designed modular with the possibility to replace damaged or to reuse intact components. The focus was here especially on the side crash protection and a reuse-friendly design. Here you can see the finalized design for the innovative cell structure. The impact energy is primarily absorbed by the CFRP crash tube using the inversion mechanism. Situated between the cover and the crash tubes, you will notice an auxetic structure. And this is a special element. It serves as a buffer and also as a force introducing element. Overall, we can say this design is a modular, detachable design, a reuse-friendly design. These are the results for energy absorption and intrusion for the defined side pole impact scenarios C1, C2, and C3. The criterion with a maximum intrusion of 218 millimeters was not violated, so we have achieved a functional proof for the new cell structure. Here you can see the causal vehicle platform in its entirety presented as a demonstrator. Dimensionally, it corresponds to a VW-T5. 7 partners were involved in the project, and within the project, we developed 3 main modules: the front-end module, the middle module with the cell structure, with plenty of space for the energy storage, and the rear-end module. We have defined many interfaces where components can be exchanged, allowing the platform to remain in operation for over 1 million kilometers. And the debut of this demonstrator occurred last year at the Hannover Messe. 2 modules, as you can see here in this picture, the front-end module and the middle module with the cell structure can be viewed at our facility at Fraunhofer IWU in Chemnitz. So if you like to see it, just contact me and we will make it possible. And here's a diagram illustrating the environmental impact. This is the result of an LCA analysis, considering 3 life cycles and a service life of 30 years. Emissions for production, use, and disposal were determined for 3 scenarios. The scenario A corresponds to the causal platform, and B and C to conventional platforms. And as you can see, there is a significant advantage of the causal platform as the closed loop system can reduce environmental impact by approximately 60% compared to conventional platforms without closed loop systems. Yeah, and additionally on the right side of the image, you can see the design studies for the construction as a bus, transporter, or pickup. We are very flexible with the platform. Currently, as my colleague Vanessa mentioned, there is further development of the crash tubes taking place in the EU project Salient. It involves an innovative front-end structure. We aim to use thermoplastic systems as a matrix materials to increase the recyclability of the components and thus become even more sustainable. The project engages partners from 7 countries, and the results will be progressively published on the project website salient-project.eu. I also extend an innovation for you to visit the website and explore further. In Salient, our institute is involved in structural concepts, design and optimization. Additionally, we will lead the manufacturing of the prototypes which has already started. As you can see, we have already designed and optimized the new CFRP crash box with an inversion mechanism for a novel front-end module. We can achieve weight savings up to 61% compared to the original steel crash box. Furthermore, we will manufacture the structure using a winding process followed by performance testing. We are also developing an active system utilizing piezoelectric actuators. This system is designed to move the front-end structure slightly towards the crash partner during an oblique crash, thereby enhancing crash worthiness. Maybe I can show you next time this development. And here are some references to my presentation. I'm happy to provide them upon request. And yeah, thank you for your attention. If you have any questions, please feel free to ask now or later via email. Thank you.
Thanks, Patrick. Interesting results. Now we move to the Salema project. Salema is about new aluminum alloys for sustainable electric mobility. The presentation will be given by Manel da Silva. Manel is the head of the Light Alloy Research Unit at Eurecat. So Manel, welcome. Please share the presentation.
Yes. Okay, thank you very much, Daniel, for this kind presentation. Everybody can see the screen?
Yes, put in presentation mode, please.
Yeah. Okay, is that right?
Perfect, Manel.
Okay, so yeah, thank you very much, everybody. Good morning. I'm the, well, as Daniel said, the responsible of the Light Alloys Research line here at Eurecat, and also the technical coordinator of the Salema project. And I will give you a short overview of the project results. Salema is close to the end. It's finishing this month, end of April. So we have more or less the project close to the conclusion, and well, we have some nice results to show you. Here you have the outline of the presentation. So I will start with project introduction, and then we'll go to the other points where the results are going to be presented. So let's start with this project introduction. So Salema is related with the dichotomy that posed the European Green Deal, where in one hand we need lightweight and high performance materials, and on the other hand they are requesting for decrease the dependencies on imported raw materials. So this is most of the times, well, quite difficult to deal, because new materials and high performance materials usually require from raw materials imported from outside Europe. So in Salema, we are dealing with aluminum alloys specifically, and we are trying to develop a non-CRM, non-critical raw materials dependent aluminum ecosystem. For that, we are exploring two different approaches. The first one is to substitute the elements that are considered critical by other elements that are more commonly available in Europe. And the second one is by harvesting these elements from domestic scrap, so from end-of-life scrap that usually leave Europe towards less developed countries, especially towards Asia, towards China, India, and so on. In the project, we are a total of 16 partners covering the whole value chain. And we are working on 3 different processes that it's about 95% of the aluminum present in the car. It's formed by one of these processes. High pressure decasting, okay, stamping and extrusion. For each of these processes, we have on one side the material development company, the company that is producing the aluminum alloy. We have research institutions assisting this company on the development of the new aluminum alloys, but also to assess the end users on the optimization of the processing of these alloys. And then, so we have the industrial partners that are giving are producing demonstrators and validating the performance of the new alloys developed. There are other partners doing some additional activities like standardization or dissemination. And a very important role is covered by these two partners, University of Liège and Comet Treatment, that are working on the sorting of the end-of-life scrap. It's one very important key point in order to have high-performance alloys from end-of-life scrap, to sort it and control the chemical composition of this scrap, as I will show you later. In the project, so as I mentioned, we are working on 3 different processes, actually 4 pilots, let's say. One high-pressure decasting pilot plant, or actually there are 2 different partners working on high-pressure decasting, then cold and hot stamping and extrusion. And we are producing 5 demonstrators in order to validate the alloys. Okay. By high-pressure decasting, we are producing a shock tower. Then by cold stamping, an inner hood, and by hot stamping, a B-pillar or part of a B-pillar. And by extrusion, a battery box profile. And also there is a frontal frame that is produced partially by high pressure decasting and partially by extrusion. It's formed by 2 parts that are welded together, and that are the base for FlexCrash project that has been shown previously. Okay, so that's a little bit the objective of the project and an overview of the structure. So as I mentioned before, we work on 2 different approaches. One is by using recycled alloys, and the other one is to formulate new alloys looking at the critical raw material content of these alloys. Okay, so I will speak about both in the next 2 points, but focusing on the development we carried out for high pressure decasting. Okay, we don't have time to go in detail to all 3 processes, so I have choose to focus on high pressure decasting. So as I mentioned before, there is end of life scrap, and what we are trying to do in Salema, it's to to harvest, to obtain the valuable part of this end of life scrap and produce aluminum, high performance aluminum alloys. Regarding emissions, energy consumption, it's clear the benefit to use recycled aluminum instead of primary aluminum to produce the high performance alloys. So, and to get this good scrap from end of life, what we use, it's the Zorba stream from Comet, that it's the stream where all the metallic and non-ferrous fraction, at least the part that is not magnetized, so not attracted by a magnet, it's this fraction. And here, University of Liège has developed this picket sorting that has been focused on aluminum, and they have been able to extract 5 different fractions, 2000 series alloy, 5000, 6000, and 2 casting fractions, one with high iron content and one with low iron content. This system, just a very high-level overview of how it works. It has different sensors, a 3D camera, infrascopy camera, so infrared camera, an X-ray, and the most important thing that it's a laser-induced breakdown spectrometer that captures the chemical composition of the fragment. So with all this data, it's processed all in an artificial intelligence model. Okay, and with these algorithms, it gives information on the sorting, on the robotic arms, about how they have to pick the piece, and especially the most important thing, in which bin they have to deposit it, so to which fraction it belongs. And here you have a video where you can see the robotic arms working at real time, so they are pretty fast. And well, with this prototype, they are able to sort about 500 kilograms per hour. So in industrial level, they expect to scale up to a higher level. Okay, so we have this part about scrap sorting. Then what we have also done is to create aluminum high performance, high pressure die casting alloys more robust to this scrap, so that can allow be produced easier with a high amount of scrap. So we have worked on the effect, so analyzing the actual effect that the impurities of a high performance aluminum alloy, as can be, well, the most typical, it's this ENAV 43500. Okay, it's aluminum silicon 10 magnesium alloy. And what we have done is work on well, increasing the level of copper that, according to the standard, should be below 0.03%, zinc, and also iron. Okay, and one important development we have done in the project is to measure the alloy flowability. We have developed our own test that is currently under a standardization. So under a, we are currently publishing a QA, a CWA from this test, and that has allowed us to predict, for instance, the loss of flowability that some minor additions. Here we can see that small additions of zinc greatly reduce the flowability of the alloy by a half. So it's, well, very important issue, not just the fact that the increase on impurities will have on the mechanical properties of the alloy, which, well, remain more or less constant, that we have also checked it, but also the castability or the processability of these alloys. Working on this alloy, so first, in the previous stage, we cover 15 different compositions, and then we select the most promising ones, and we went to our high pressure casting machine, and we cast testing samples, plates, that give us an idea of the properties we could reach on the final demonstrators. So with those plates, we calculate the mechanical properties, and we observe that the values were pretty good. Here you have the requirements of our demonstrators, the shock tower proposed by Ford and the frontal frame from Stellantis, from Fiat. And we could meet the requirements from the shock tower in terms of yield strength and ultimate tensile strength, even without heat treatment for most of the alloy variants. We had bigger problems with the requirements from the frontal frame, but with a heat treatment, we should be able to meet it. And actually, we were able to meet these requirements. The main issue was related with elongation, but well, we are going to deal with that later on. We also measure the corrosion resistance, because it's one other important aspect related with impurities, especially copper, reduce aluminum, well, the corrosion resistance of aluminum alloys. Here we observe that the amount of copper, or the increment of in impurities, didn't affect that much on corrosion resistance, and the weight loss was more or less the same. And well, unexpectedly, we observed that the heat treatment highly improved corrosion resistance. So a T6 heat treatment will lead to better corrosion resistance regarding to as-cast properties. And this heat treatment was much more important than the impurities we will have in the alloy. Okay, so that was regarding the development of partially recycled alloys. So I will shortly explain also about the procedure we follow for new formulation, for formulating alloys with lower critical raw material content. So the first thing we did was to go into the list of critical raw materials posted by the European Commission, and we developed a way to calculate the criticality of these alloys. Okay, so we had this criticality index that it's just we're weighting the composition of the alloy and how critical the different elements are, and then we elaborate the castability of this alloy with the use of thermocalc software, so by thermodynamic simulation, and in some cases elaboration. So as example here, for instance, in order to determine the hot tearing, the tendency of hot tearing, we define from the solidification curve the gap, the temperature gap between the 95 and the 100% of solidification. That gives us an idea of how will be the hot tearing of this alloy. Okay. And so with all this data, what we did is for over 150 alloys in total, about 70 for high pressure decasting, we weight, so we calculate the critical index, taking into account the amount of magnesium and silicon present in the different alloys, mainly, that are the two critical elements most common present in aluminum alloys. And then also we predict these 5 factors: the viscosity, shrinkage, sludge factor, die-soldering, and hot tearing. We weighted 1/3 for the criticality and 2/3 for the castability. So the processability is more important, that it's being able to be processed than if it's critical or not. And we give a value, a score to each of these over 70 alloy variants that we test. Okay, from that we select 2 families. Okay, aluminum silicon 8 manganese magnesium and aluminum magnesium families for further development, and we went into a high pressure decasting machine also with testing die and produce for 7 different alloys variants, parts, and we measure the mechanical properties achieved. With those alloys, we observed that most of them were, as in the previous one, meeting the requirements in terms of yield strength and ultimate tensile strength of the shock tower. But we had more issues regarding the frontal frame. Okay, but also with a T5 heat treatment, we expected to solve this and cover the gap between the actual mechanical properties and the requirements. Okay, so, and this is a little bit the procedure we follow, very fast explained because we don't have much time. And what I want also to show you is the results we achieve in 2 of the validations, in 2 of the demonstrators we use in Salema. For high pressure decasting, I have selected the shock tower. Okay, the other demonstrator that is not present in FlexCrash. For this demonstrator, first we use the benchmark alloy, the standard EN AV 43500. With this alloy, we were getting these mechanical properties in the scarce condition, and after the heat treatment, we were reaching the requirements of the component, that it's 120 megapascals, 180 megapascals for ultimate tensile strength, and 10% of elongation. Okay, so 120 for yield. Once we had this good result with the benchmark alloy, we move into adapt the production process to the new alloys. For that, the first thing we did was to characterize the some physical and thermal properties required by the simulation software in order to have experimental data to fit the simulation software that will provide us more reliable results that just the database data for the benchmark alloy, for the standard aluminum silicon 9 manganese magnesium or silicon 10 manganese magnesium. And with this data, we ran out simulations. We were able to see that, with the reduction of silicon, we will have more issues regarding temperature. So we will need to increase temperature or injection speed in order to have a good soldering here in the back of the part. Okay. And also some similar problem we will have with the aluminum magnesium 2 alloy variants. Okay. Actually, with that was already predicted by Thermocap, the main issue was hot tearing, cracking during solidification. And just to shortly show you the results we achieved. So with variant 6, that it's a variant produced with about 90% of end-of-life scrap, we were able to have mechanical properties close to the benchmark, to the standard alloy. Okay, the elongation was reduced slightly, about 10%, but also we had a small increase in yield strength. And after the T7 heat treatment, we were meeting the requirements of the demonstrator: 120 megapascal for yield, 180 for ultimate tensile strength, and 10% of elongation. Okay. We also tried an aluminum silicon 10 manganese magnesium variant. With that, elongation was closer, so we wanted to try a different approach that it's more better seen by end users. Instead of a complex T7 heat treatment that requires heating at very high temperature, we went for a short annealing. And with that, we observed, we test 2 different temperatures. With the first one at 320 degrees, we didn't see any improvement in terms of mechanical properties. And for the second one at 380 degrees Celsius, we reached the required elongation, but we lost some yield strength that went below the minimum requirement. And finally, regarding aluminum magnesium 2 alloy, the alloy that we test, we had some issues regarding yield strength. In some of the regions of the shock tower, was possible to obtain or almost reach all the requirements without heat treatment. But as I mentioned before, we had some hot tearing problems with this part, and with this complex shape, a lot of cracking was observed, and there was a high dispersion, because if we tested a cracked part, of course, the mechanical properties went down a lot. And then also we have taken into account during the whole project the life cycle assessment and the global warming potential of these alloys, and we see that these alloys have a very good potential regarding this aspect. They are much greener than the standard alloy. We can reduce almost 75% the global warming potential if we are using the variant 6, that is the one that we have seen previously that have reached all the requirements. So we are pretty happy with the results. And finally, I wanted also to explain you a little bit about another technology, the research we have done in hot stamping. that it has been, well, we are very glad with that. For hot stamping, we have tested 2 different alloys, well, actually in a stamping, 6,000 alloys where we produce them with 3 different levels of recycled content, okay, and 5754 alloy with that were produced with 2 different levels of recycled content. In the 6181, in order to reach this level of recycled content, it was necessary to increase the amount of impurities present, iron, copper, manganese mainly. We also increased magnesium and silicon in order to compensate, and well, also some zinc was increased. In 5754, almost it was possible to produce with very similar level, just some higher iron was required. The mechanical properties in terms of tensile test were just very similar. So the fact to increase the level of impurities didn't really affect the mechanical properties, even if we were cold forming or hot forming these alloys. But if we look at other properties, as the essential work of fracture that was probably presented by Sergi earlier this morning, we observed that for the 5754, there were almost no difference. There was a cloud of points that could perfectly be from the same material. But on the 6181, we had 2 different behaviors, okay, that these were related if we went on formability, alloy formability, on differences on the formability test curves. So here on the right, you can see clearly how the type 1 and 2 for 6181 decrease the formability. But even if they exhibit worse formability, if we put all together in one single chart, we can see that these new 6181 alloy variants have a close formability to the 5754. So not big trouble or not big loss of formability. So we can still deal with them and work with these alloys, and that's what it was done with the data extracted from EureCAD tests and also some tests done by Gestamp, okay, tensile tests at different strain rates and different temperatures, and also these friction tests carried out at Gestamp. There was performed the simulation of the demonstrator. Some critical areas were found that just with some minor changes were solved, and with that data, the tool was manufactured and the production of the demonstrator was done. That is currently being checked, and well, the mechanical properties are being determined. So, but we are very happy with those results. So the shape was fine. In terms of methodology, results are perfect. And right now we are checking the mechanical properties and assessing the performance of these new alloys. And with that, I have finished.
Thank you, Manel.
Thank you very much. Well, thank you very much, all of you, for your attention. And well, if you have any question, I think later on there is.
Yes, we have later question and answers section.
Yeah.
Okay, now we move to the Flamingo project. It will be presented first by Alvise Bianchin, R&D project manager at MBN Nanomaterialia. So welcome to this conference, and yes, please see the presentation.
Thank you for having me today.
Yep, go ahead.
Perfect. So as said, I'm project manager here in MBN Nanomaterialia, which is a company based in Italy, and also a producer of advanced materials, primarily for the powder metallurgy sector. We are also a coordinator of these projects, fabrication of lightweight aluminum metal matrix composites, and their validation in green vehicles. So a bit of context for Flamingo, which is actually the same of all the other projects, and the main reason for which we are here today. Due to the fact that vehicle lightweightening is particularly sensitive in battery electric vehicles, the use of aluminum as a vehicle component is growing. I put together some data from the raw materials information systems. These are referred to the overall tonnage of materials used in battery electric vehicle fleet, which is running in the different years. And we can see that there is a steady growth for all the materials. Although the aluminum, the wrought aluminum and the cast aluminum has, let's say, quite different degree of growth in terms of amount. There is a possibility for aluminum to tap into this mild steel range if we could have an aluminum with the correct and exact mechanical properties. So one question that we made us from the beginning of the project is how can we make a stronger aluminum, considering the strengthening mechanism that are already considered for aluminum, such as the hole patch and the R1 mechanism. We realized that all these are basically derived from the availability or the creation in the melt of nanoparticles. This is well known, and this is also possible to reach thanks to the direct inclusion of nanoparticles in the alloy. And this produces a similar strengthening mechanism and similar effect on the overall alloy. So why should we focus on nanoparticles? Well, this could give us the possibility to be less dependent on alloy composition. So as said, also in the Salema project, this has been developed to be trying to be less dependent on this critical raw material and finding other ways to develop alloys that has good mechanical properties. The inclusion of nanoparticles could avoid and limit the thermal treatments, since the development of nanoparticles is still there since the beginning. Nanoparticles doesn't need to be precipitated in the melt with the thermal treatments. And the inclusion of nanoparticles means that the elements in the overall aluminum matrix can be the same and compatible with the current available aluminum alloys. Ideally, this would allow us to compete with more steel components and substitute them in cars. So if this is quite convincing as an approach, then we need to identify which nanoparticles to use. So the boundary conditions for this is that nanoparticles should be easy to disperse. They should have similar densities of the aluminum melt, good wettability in the melt, and also good stability. So not particularly, not breaking up in the aluminum due to the temperatures that are present. More than that, the nanoparticles should be safe. safe for the workers and in all the manufacturing steps. And also nanoparticles should be affordable. Finally, what we should also consider for any material development is that the new material has to be recyclable. So the new aluminum metal matrix nanocomposites should also comply with the current technologies for recycling. So in Flamingo, we considered a couple of approaches to tackle these requirements that we had since the beginning. One is the use of predispersed and concentrated additives that could ease the dispersion of material and can also resolve the problem of safety, since nanoparticles can be embedded in the aluminum since the beginning. And then to make them affordable and recyclable, we considered since the beginning to have expandable nanoparticles, in the sense that nanoparticles will be lost at the end of the overall process and of their life cycle. So the life cycle I was speaking about that we have in Flamingo is this one, considering nanoparticles creation in the master batches that are used in foundries to make melt, that are used in DC casting for extrusion, Greensen casting, low pressure die casting, high pressure die casting. The component design is obtained also considering topology optimization. And then there is the use of the components in the vehicle. Eventually, the components is recycled, and throughout all the life cycle, we are considering the safety aspect as well as the overall costs and environmental costs. So today we are a bit more focusing of titanium carbide particles and nanoparticles in this project, although in the project we developed also silicon carbide nanoparticles, and we tested also aluminum oxide nanoparticles. The project is 4 year long. We are basically 3 years and something on the path, so we are ending in the next January. 11 partners, most of them are industrial partners to cover the different technologies that are involved in the project, such as the extrusion by Constellium, high pressure die casting by Brunel University, Greensen casting, low pressure die casting by OGE, and the manufacturing of the master batches by MBN, the recycling by Campacas. There are also, beside all these technologies that I just mentioned, there are also partners focused on the activities supporting the results, like IP, training, LCA, standardization, etc. So since we have not much time today, I just want to focus with a couple of slides on the production of the nanoparticles master batches and their recycling. My colleague Abdallah after me will talk more about how these are used for the DC casting and extrusion of parts. So about the production of master batches, one thing that is related also with the safety is that nanoparticles tends to be quite volatile and are generally dealt that with in a way that minimize as much as possible their release in the environment. So beside that, they are also difficult to be handled due to their dustiness. And a way that we developed in MBN to include them in the master batch is their direct synthesis at solid state by a mechanical alloying in the aluminum matrix. And we can reach that with a concentration of titanium carbide, which is up to 80% in weight. And for the purpose of ease the dispersion in the final alloy, we dilute it up to a content of less 45 weight percent. As you can see, the distribution of nanoparticles and submicroparticles is quite broad. There are different many particles around the micron size and many more which are below the 100 micron. And this particle size distribution also affect the overall properties eventually of the materials, with some tendency of the smaller particles to degrade and the titanium to be released in the final melt. This approach couldn't be followed with the silicon carbide, although we are still on the development of a similar process for that. And for that aspect, especially for the safety concerns, this was quite effective. Going to the other end of the life cycle of the process, we can give a look on how we tackle the recycling. So the idea here was to apply the standard recycling procedure, since we know that our materials, if we are successful and we can introduce them into the market, they will need to be dealt as standard aluminum components. So we try to check what happens if these materials ends up in a foundry and recycled. So the standard procedure considers the an initial melt with the removal of scrap and the flux addition to form a protective cover and minimize the oxidation of the melt, and then skimming a couple of times with the addition of nitrogen in the form of tablets. What we end up with is a billet on which we can perform some characterizations. The two main characterization methods that we used are the hardness test, which is an indirect way to measure if nanoparticles are still there, since they affect a lot the overall hardness of the material. And this is most effective when we have elements in the nanoparticles that are matching with elements in the aluminum alloy matrix. In the case where the elements are not matching, then we can use the optical emission spectroscopy to assess the amount of, for example, titanium, which is directly related to the titanium carbide in the material. And as we can see already from the first fluxing with nitrogen addition, these were basically going back to the original state without nanoparticles, further confirming that this approach is quite usable for as a strengthening mechanism in the current uses of aluminums. Few words about also the evaluation of safety. This has been done basically for exposure control and during different operation of the nanoparticles introduction, and in the first step, the casting, the welding, and now is being done also for the recycling step. This is this controls the exposure, so the release of nanoparticles in the environment. And an important thing is the capability, the possibility to distinguish between accidental nanoparticles and engineered nanoparticles. So the benchmark between the process without alloys containing nanoparticles and those containing nanoparticles, since the basically any operation in the industries might and is effective in creating airborne nanoparticles, which sometimes are not directly related with what you are actually using as material. So just a quick slides about some of the interesting results that we had in terms of increase of heel strength and ultimate side strength for different condition. We have now realized this steering knuckle, which can have different weight savings due to the different topology optimized geometries. The other component that we are realizing is the rear frame, which is obtained by extrusion, and also this one is heading to have a weight decrease of 35% compared to the current component for this vehicle, which is made in steel. Good. So I gave you an overview of the Flamingo project with a couple of insights on the master batch production and recycling, and I will leave to my colleague Abdallah to talk about some technical details on DC casting and extrusion with titanium carbide.
Thank you. Yeah, thanks for this interesting presentation about the Flamingo approach for lightweight. Now we close the session with technical presentation. Going to be given by Abdallah Abu Amara, a doctoral researcher at Brunel Center for Advanced Solidification Technology. Welcome, Abdallah. Please share the presentation.
Thank you. Hi, can you hear me well?
Yeah, I can hear you.
Okay, great. Share the presentation. So you can see it in full screen?
Yes, perfect.
Great,
Go
great.
ahead.
Thank you. Thank you for the introduction. Yes, so my name is Abdullah, and I'm a PhD student at the Brunel Center for Advanced Solidification Technology. And Alvis just did a really nice summary of the Flamingo project. So I won't talk more about the kind of overall summary of the Flamingo project. I'm going to go more into detail about the technical activities that we've done. So the title of my presentation is the microstructure and mechanical properties of 6000 series alloys reinforced with ceramic nanoparticles. And just to start off with, I want to just give a quick brief introduction to what BCAST actually is. So the Brunel Center for Advanced Solidification Technology, or BCAST, is a research institute, and it focuses both on the fundamental and applied research on solidification of metallic materials. And initially, BCAST was created in 2002, and it only had a handful of staff and PhD students. But over the past 16 years, it's grown to, we have now 85 personnel plus 15 seconded industrial research engineers. And BCAST currently is a dominant research group in its field in the UK and one of the largest in the world. We have more than 4,000 square meters of laboratory space and over 43 £1 million of capital investment. So you can see here we have some, sorry, I'm just going to put my pointer on. Here you can see here we have some, these are images of some of our facilities. So we have an advanced materials processing center. We have an advanced materials casting center, which has a HPDC caster. We have a low pressure die caster. We have some sand casting facilities. And most importantly for today's presentation is the direct chill caster. So this is the industrial scale direct chill casting machine that we have. So I'll be talking more about direct chill casting in the few slides later on. To kind of tell you what the part that we play on the Flamingo project and what we do as BCAST. So the aim is to really produce high specific strength aluminium metal matrix composite parts, and for these to be used in electric vehicles. So as you all know, 6000 series alloys are commonly used in the extrusions and body in white for the automotive sector. So you can see in the figure some of the extruded parts in blue which are used. And the idea is for us to use these 6000 series alloys and to add the reinforcement particles to them so that we can increase their strength. So in terms of the raw materials, we have worked with 3 different 6000 series alloys, which were provided to us by our partners Constellium. And these were the HSA6370, the HSA6340, and the HCA6300. And all of these are 6000 series alloys. The first 2 are high strength alloys, and that's why the code is HS for high strength. And the final one is a high crushability alloy. So I guess this is probably more of an interest for you, since the FlexCrash project is focused on crash management systems. So as for the reinforcement particles, we were provided, which were provided by MBN, we were provided with 3 different types of particles. So alumina, aluminium oxide, Al2O3, silicon carbide, and titanium carbide. And the reinforcements are provided to us in the form of master alloys, as Alvis already mentioned. So the master alloy essentially is an aluminium X weight %, either alumina, silicon carbide, or titanium carbide. So here we can see the microstructure. These are titanium carbide particles, and you can see the matrix in the background is aluminium. So for the purpose of today's presentation, I'll be focusing on some of the results which we achieved with the HCA6300 alloy and with the additions of silicon carbide and titanium carbide, since we got some interesting results with these. So to quickly share with you the methodology that we use and how we actually process the materials and prepare them. So the first step in our experiments is to prepare them out. So essentially we heat the 6000 series alloy to 730 degrees in an electric furnace. Then we can add the master alloy containing the nanoparticles. So we wrap the powder in foil, and as you can see, we pour it directly into the melt. So this would be the powder containing nanoparticles. And during this action of pouring the powder into the melt, we apply mechanical stirring. So essentially we have a rotary device connected to an electric motor, which stirs the melt, if you like, and kind of aids with the introduction of the particles into the melt and with the dispersion as well. So the titanium carbide particles have a mean ferrite diameter of 1 micrometer, and the silicon carbide particles have a mean ferrite diameter of 100 nanometers. So you can see the silicon carbide particles are a lot smaller, meaning sometimes we have to apply different stirring times. So we stir them out for different periods of time in order to get all of the powder in. The third step is typically the ultrasonic treatment. So essentially we apply some ultrasound waves in this composite melt. And the idea is to produce some ultrasonic cavities that can then disperse the particles even further. We really need a homogeneous distribution of the particles in the melt in order to achieve the best mechanical properties. If we have agglomerations or some clusters in the melt, then that can create weak spots in the material once it solidifies. So this is why we try our best to achieve the most homogeneous distribution of the particles. So we apply the ultrasound for approximately 10 minutes at a frequency of 17 kilohertz. And then the next step is the actual casting itself and the characterization. So let's take a look at what that looks like. So once we have the composite melt, we can pour it in this keel die, which has this shape, as you can see here. And we can produce these aluminium composite material castings. Once we have these castings, we can then characterize them using optical microscopy, SEM, XRD, and so on. And we can also machine some tensile bars for mechanical testing. So you can see it's quite convenient because we have this round section at the bottom of the die. So we can quite easily machine some tensile bars for tensile testing. So in terms of the materials that we actually produced, this is, let's say, a quick summary. So for the materials containing titanium carbide reinforcement, first of all, we have to cast the reference alloy. So just the HCA6 300 by itself without any additions. And then we cast the alloy with the addition of 0.1, 0.3, 0.5, 1, 2, and 5 weight% titanium carbide. And for the silicon carbide, again, we cast the reference alloy, just the HCA6 300 by itself. And then we also added, in this case, for silicon carbide, 0.1, 0.3, and 0.5 weight% silicon carbide. So the reason why we were only able to go up to 0.5 weight% silicon carbide, whereas with the titanium carbide we're able to achieve more, is related to the wettability of the materials. So as you can see here, I've put the wetting angles for an aluminium silicon carbide system and the wetting angle for an aluminium titanium carbide system. And you can see that the wetting angle for the silicon carbide is much higher, 79, whereas for titanium carbide, 60. So what this means essentially is easier for the melt to accept the particles, if you like. It's easier for that liquid melt to wet the particles. So we're able to achieve these higher weight percentages with titanium carbide. And for each composition, we tested 5 samples in the as-cast state and 5 samples in the heat-treated state after heat treatment. So now we can take a quick look at some of the results. So these are some microstructures from the castings which we produced. In the top row, you can see the base alloy without any addition of reinforcement. And in the middle row, you can see the microstructure of the castings containing silicon carbide reinforcement. And in the bottom row, you can see the microstructures of the castings containing titanium carbide. So you can see for the reference alloy, or for the base alloy without any addition of particles, this had the typical 6000 series alloy microstructure with some of the typical phases present, such as the Mg2Si and the eutectic alpha phases, the Q phase, and of course the iron-rich phases as well. With the addition of the silicon carbide particles, we saw that the silicon carbide particles appeared in these relatively large agglomerates. So you can see actually when we increase the magnification on this agglomeration, you can see the individual silicon carbide particles that can be identified. The reason for these agglomerations is because, as I mentioned previously, the silicon carbide particles have smaller sizes than the titanium carbide. So what that means is essentially there are higher, the van der Waals forces in between the particles are stronger. So it's more difficult to break these agglomerations apart or to disperse the particles. And we also saw the spinel phase, the MgAl2O4. Essentially, the reason why these particles appeared is because of the extended stirring time. So the longer we stir the melt begins to oxidize and we form aluminium oxide. Then this aluminium oxide can react with the magnesium, which is inherently present in the alloy, and it can form spinel. And as for the castings containing titanium carbide, luckily we didn't see any particle agglomerations. The particles tended to appear in these particle-rich regions, but they weren't agglomerated. We can actually identify the individual particles freely present in the matrix. So this was a much better distribution than the silicon carbide particles. We also saw, quite interestingly, these large blocky titanium alumnide phases, or Al3Ti. And the reason for this phase forming, is because of a reaction between the titanium carbide and the aluminium matrix. So post heat treatment, once the material was then heat treated, of course, we characterize the microstructure again. And as expected, the large coarser Mg2Si phases and the copper-rich phases, they had dissolved. And what we mainly had left were these iron-rich phases. And of course, we also formed some precipitates, and these precipitates aid in the strengthening of the material. And speaking of strengthening, I can quickly talk about some of the tensile properties that we were able to achieve with the additions of titanium carbide and silicon carbide reinforcements. So In the top row, you can see the tensile properties of the castings containing titanium carbide. On the left-hand side, this is the as-cast material. And on the right-hand side, this is post-heat treatment. So once the material was heat treated and tested again. And in the bottom, you can see the same for silicon carbide. So this is as-cast and this is heat treated. So with the addition of 0.1 weight% titanium carbide, we were actually able to achieve a 20% increase in the yield strength of the material. So this was quite impressive considering that the alloy is already quite optimized. And once the material was then heat treated, then this increase was reduced slightly. So instead of a 10% increase in yield strength with 0.1, instead of 20%, we were only able to achieve a 10% increase with the addition of 0.1 titanium carbide, which again is still quite significant considering that the alloy is optimized. But the reason why this increase was reduced is because other strengthening mechanisms which are inherently present in the alloy are kind of taking over and outweighing the nanoparticles that we added. So, for example, the precipitates forming and for example, the strain hardening effect. But nonetheless, we still managed to achieve a 10% increase in the yield strength with the addition of 0.1 weight% titanium carbide. And with the additions of silicon carbide, we weren't able to achieve any increases in the yield strength, neither in the as-cast state nor in the heat-treated state. And we attributed this to the large agglomerations which we saw in the microstructure. So what does this mean? How does this help in any way? So essentially what we want to do is we want to apply, or let's say, take these same principles and these same results that we achieved with the titanium carbide and replicate the methods and the results in direct chill casting. Essentially, direct chill casting is a popular way for mass producing aluminium, especially aluminium billets for the purpose of extrusion or rolling. The idea is, so direct chill casting is a method that begins with melt being poured through a water-cooled mold, as you can see here. So this is the aluminium melt in red. And essentially the melt travels down and it goes through this water-cooled mold, and then it goes to this dummy block. Essentially, this dummy block begins at the top, and the melt begins to solidify and the dummy block begins to move downwards. So as the dummy block moves downwards, water is sprayed on the billet, as you can see here. And so it begins to solidify very quickly and the cooling rate is very fast. So what we get forming is a high strength billet with a fine microstructure. And you can see this is an image of the direct chill casting facilities at Brunel. So we have here, you can see the hot top and the aluminium melt. And this is the water from cooling the billets. And this is one of our composite castings, actually. We had applied ultrasound, you can see, in different areas in the launder and the hot tops for dispersing the particles. So essentially, as I mentioned before, we wanted to apply the metal matrix composites technology in direct chill casting in order to be able to move forward in kind of industrializing the aluminium metal matrix composites technology. So we were able to produce some pilot scale preliminary DC cast billets. So you can see this is a 2 meter long direct chill cast billet, and we had added titanium carbide particles, and we were able to identify these titanium carbide particles in the microstructure. So we had successfully incorporated them in the DC cast billet. And then these billets were then extruded by our partners, Constellium. So essentially, they were put through the extrusion die, and we had some preliminary extruded material, which we're still kind of optimizing the process and working on it. But we have some preliminary extruded material that contains titanium carbide particles and some pilot scale direct chill cast billets as well. So to kind of summarize what's been mentioned, the following points can be said. So titanium carbide particles seem to be a suitable addition for 6000 series alloys, and for the purpose of increasing the mechanical properties, and in particular the yield strength. And silicon carbide particles didn't result in the improvement that we saw with titanium carbide because the silicon carbide particles had agglomerated due to their smaller sizes. And preliminary pilot scale aluminium composite direct chill cast billets incorporating titanium carbide particles were produced, and these also were extruded successfully. And this is all in an effort to kind of upscale and industrialize the metal matrix composites technology. And thank you for listening. I think there is a Q&A session now, I believe.
Thank you. Very, very interesting and inspiring talk. That was really nice results and promising. Okay, now I would like to ask the presenters to be here in the table. Okay, it is not possible. Next time we have to organize it presentially. I think it would be better. But yes, it's time for the question and answers. First, because we have here the audience patiently waiting. Some of our Swedish friends are really hungry, I know, but they are still here. So please, I would like to ask first to the audience if there are any questions for our presenters. Yes, we have a question. Francesco, please go ahead.
Can you hear me also online? Yes.
Can you hear Francesco online?
Yeah.
Perfect.
So I have a question for Abdullah for the last presentation, because at the beginning of the presentation, you showed that you had different choices of aluminum alloys, mainly within the 6000 series, but then you decided to go on with the crush-worthy alloy rather than the high-strength ones. But it didn't get the reason why you chose that way.
Yeah, so the reason is to do with the surface tension of the alloys. We found that this high crushability alloy had less surface tension essentially, so it was more accepting of the particles, right? So it was easier to incorporate the particles and include them in the high crushability alloy when compared to the high strength alloys. And this is the main reason is related to the chemical composition. So the chemical composition has a direct impact on the surface tension of the alloys. Essentially, it's related to which other metallic materials you have, or which other alloying additions you have in the material. And the high crushability alloy gave us the best surface tension. And another reason is because the high strength alloys are already very optimized for high strength. So they already had inherently some, let's say, nanoparticles present post heat treatment. So we have, for example, the aluminium, zirconium, the AO3ZR, which are really fine nanoparticles already present in the alloy, and that means that it's much more difficult to increase the strength with the addition of our nanoparticles. So it's easier to increase the strength of the high crushability alloy.
Yeah. Just to go on with the question, when you said that it's ideal, the surface tension is because it's lower or higher?
Lower, yeah. So we need lower surface tension. So if we have a surface tension which is lower, then the alloy can wet the particles easier. If we have a higher surface tension, then the wettability is poorer.
Okay, thanks.
Thank you for your question.
Some more questions? Well, I can consider myself as part of the audience, then I can have a question as well. It's addressed to the Flamingo friends. I don't know if for Alvise or for Abdullah. Is you show the potential for these materials to be served as extruded tubes or profiles and castings. Have you explored also thinner formats like sheet metal plates?
No, actually not. We know that the formability of these alloys with nanoparticles is reduced, and we thought that well, having all these casting technology plus extrusion was enough for the project. So yeah, we don't have information about the casting of flat plates.
Yeah, I understand. It's a novel approach, so that would be enough. Maybe for the future, hot stamping of aluminium plate or aluminium sheet will be interesting to overcome, as you said.
Definitely.
Yes, can be. And also, have you considered using for the additive manufacturing as a powder?
No, well, we considered in the sense that we know the inclusion of nanoparticles affects the formation of crystals, so it refines the crystal structure of the alloy, and this is helping when you are dealing with melting and remelting of the materials during the additive manufacturing process. So we know it might be interesting there, but we didn't test it.
Exactly. Next step. Perfect. Thanks. Now, back to some questions from the online this time. First one is for Vanessa. Yeah, you show that the Celium project is focused on the front end structure, and the question is if the innovations are transferable to other components.
Yeah, for sure. Well, not only the eco-design approach, which is literally transferable to any kind of components of products, but also, for example, the active systems can be also transferred to, for example, the lateral components for lateral crash and so on, or the rear protection in the vehicle. So definitely, but for questions of scope and budget limitations and so on, we prefer to focus on one of the key components for safety, which is the front end structure.
Interesting. I was curious about the role of the shape memory alloys. You show which is the role of that alloys in the active system.
Yeah, they're integrated in the thermoplastic tapes components, and they act changing the strength, the stiffness. So you can, in a way, customize or tailor the strength according to a given crash or according to the angle of this crash. So the idea here is to personalize the front-end structure for a very specific crash, not only for Euro NCAP or regulations.
Interesting. We will keep an eye on your developments. Very interesting.
Thank you.
Okay, the next one is for Patrick. Patrick, yep. Can you explain the manufacturing process of the crash tubes? It looks promising, the performance, so people are curious about the manufacturing.
Well, actually, it is a winding process, and it depends what kind of matrix you use in your composite. When you use duroplastic matrix, it is a wet, so-called wet winding process, where the fibers are impregnated by the duroplastic matrix system. But you can use also, as we aimed in the Salient project, thermoplastic tapes. So the tapes are made from polyamide 6, and they are reinforced with endless fibers. And this is semi-finished product you can achieve. And you can put such a tape on a winding core and melt it with a laser system, layer by layer. So this is the technology behind this.
Okay, thank you.
You're welcome.
And the last question, this time also from the online, is for Manel da Silva. Is why this LIBS system is not sufficient alone to identify the aluminum alloy in the scrap?
Okay, well, so I'm not an expert in this picket system and this sorting, but well, fortunately, 2 weeks ago we had the General Assembly there at the University of Liège, and they, well, explain us a little bit more in detail. So it's the LIBS. It's the basic. it gives more information about the chemical composition, and it's the basis to put the scrap piece in one or other box. But the rest of the sensors are required for grabbing the scrap. So for instance, a 3D camera gives an idea of the position, and it gives information of where to hit the lips, and also how the robotic arm has to grab the piece in order to have the higher success rate, because there is they said about 5% of the scrap piece that once they try to grab it, they are not correctly grabbed and they fall. Then there is the X-ray. They give a fast analysis that can have information for the lips, and they discard with the X-ray pieces that are clearly not aluminum. So they go like that. They don't need to do the lips for all pieces, because the main limitation is the time, so the number of shots with the lips that they can do. So if they are screening earlier with the X-ray and removing some of the pieces from the lips, they can increase the productivity of the whole system. Okay, so the main information regarding chemical composition comes from the lips, but the rest of the sensors are for improving the grab, the performance, let's say the success, the success rate in grabbing the piece, and also for increasing the productivity. Okay, I hope that this answers their question.
Yeah, thanks, Manel. And also, this is any other question for the audience? Except, okay. No, this is a final question from my side, Manel, to you. You show interesting results about the performance of aluminum alloys with a high amount of recycled content. Do you think it's a limit on that? Can we go higher in recycled content?
Well, so regarding the use of recycled material, so aluminum can be recycled infinitely, and in principle you can use 100% of aluminum content. The problem is that, well, in each cycle of recycling there is some contamination, so you need to be careful in order not to contaminate aluminum, because once you have everything melt together, it's impossible or almost impossible to separate. So there are no technology to remove the elements from the molten metal once they are all melt together. So it's possible to go over this 90%, especially if you have well sorted the scrap. So if you have, for instance, if you have a scrap that you know that are from 6000 series, you can go for very high aluminum recycling ratio. So if you have extruded profile that you know it's 6061 or 6063, because all the aluminum carpentry are more or less the same alloys, and you want to produce again extruded profile of similar composition, I think you can go for 95 and 98% of recycled material.
Okay, it's clear.
Mm-hmm.
Okay, I would like to thank again the presenters. And I would like also to invite to lunch, but I know this is not possible. So next time, again, this is on our side. Yes, thank you also to the audience and the ones that are online for attending, for interesting presentations, for interesting discussions. And of course, this is just the beginning of, I hope, some more collaborations in the field of light and safe materials for automotive. So I think it's time to close the session. See you soon in the meetings, in conferences, in the beach, in the mountains. See you.
Thank you very much.
Thank you.
Bye-bye.
Thank you to all.
Thanks. Bye.